This is an aptitude question. They are saying that the ratio of boys to girls in a class is 7:3. Among the given options, we need to determine which of them can be the possible strength of this class. Since the ratio has been given as 7:3, we can assume the common factor to be x. Then in that case, the number of boys in the class will become 7x and the number of girls in the class will become 3x. With this, the total strength of the class, which is the sum of the number of boys and girls, will be 7x plus 3x equal to 10x. Now, this 10x is a product of two terms, 10 and x. So whatever the result is, that will definitely be a multiple of 10. Any possible value of x will never give us any result which will not be divisible by 10. Hence, among the given options, we see that only 50 is the one that is divisible by 10. So that will be our answer. The strength of the class will be 50. This is a question based upon spatial aptitude. They have defined a convex polygon as, for every pair of points P and Q belonging to that polygon, the segment PQ connecting them must lie completely inside or on the polygon, means as its sides. So among these four, we need to identify which of them is not a convex polygon. Let us start from here. Numbering the segments, the points as P, Q, R and S, you can see that all the segments connecting them will form either the sides or the diagonals of this polygon. So it is convex. In option C, if we have the points A, B, C and D, then again we will get all the segments lying inside or on the sides of this polygon. So this is also convex. In option B, we have the points P, Q and R and all the segments connecting a pair will form the sides of this polygon, making it complex as well. It is also a convex polygon. Now in the first one, let us name the points as A, B, C, D and E. Then here we can see that for AB, AC, AD or BD, EC, these segments are lying inside or on the sides of this polygon, but if we take the segment AE, then we can see that it is lying outside this polygon. So this is not convex, and that's what we will be reporting as the answer. This is an English aptitude question. We have been given two statements, and for each of them we need to determine if it is grammatically correct or if there is some ambiguity in them. Now looking at the statement 1, everybody in the class is prepared for the exam. This is simply an assertive sentence which is stating some fact that everyone is prepared for some exam. So there is no grammar mistake in it. It is a correct sentence. Now looking at the statement 2, Babu invited Danish to his home because he enjoys playing chess. Now here it is a little unclear what this pronoun he is referring to. If it is referencing Babu or if it is referencing Danish. If we assume that Babu is being referred by that pronoun, then it is unclear if Danish enjoys playing chess or not. So there is some ambiguity in this statement, and we can say that the statement 1 is grammatically correct while statement 2 is ambiguous. So the correct option will be C. This is a spatial aptitude question about paper folding. A round sheet of paper has been taken and initially we fold it vertically to get the shaded portion as the result. After that, in step 2, it is again folded into half to get a quarter paper, and after that we make some cuts upon that as shown over here. We need to determine what will be the outcome after this particular paper is once again opened up. So let us try to trace it out based upon this existing design. It will be looking something like this. We make it symmetric on all the four sides this way, and again take the mirror image of that. Here it will be like this, again making it symmetrically. So this should be the resulting figure, and as you can see in all the options, the only one matching with it is option A. So that will be our answer. This is a logical reasoning type question based upon analogy. We need to find out which option best fits into these particular blanks while making the appropriate analogies. Option A is plan is to surgery as writer is to outline. Surgery is done in a planned way while writer creates an outline. No, it does not suit very well. Hospital is to surgery as writer is to library. We can say surgery is done in the hospital, writer writes in the library. No, it does not make sense because actually books are kept in the library, not writer actually writes in the library. Option C, doctor is to surgery, writer is to book. Doctor does the surgery, writer writes the book. Yes, this one makes sense. Let us also look at the next option. Medicine is to surgery, writer is to grammar. Surgery requires medication, writer requires grammar. This might also work, but the best suiting analogy in this case is the third option. Doctor is to surgery, writer is to book. That makes sense, and hence this should be the most appropriate choice of our answer. So going with option C. This is an aptitude question based upon simple geometry. We have two sheets of paper M and N of equal dimensions, 6 cross 1 centimeter. Now they have said that the sheet M is folded to form an open cylinder by bringing the short edges together. These are the short edges of 1 unit. They are brought together, which means in this fashion we are folding the sheet to form a cylinder of this kind, which means the height of the cylinder will be 1 unit and the circumference of the cylinder will be 6 units. On the other hand, the sheet N is cut into equal square patches and assembled to form the largest possible closed cube. Now we know that a cube like this, it has all the sides of equal length and it has 6 sides in total. All its edges are equal in length. So using this particular sheet, if we want to form a cube, then it will have all its edges of 1 unit. Now we want to find the ratio of the volumes of the cylinder to that of the cube. So while looking at this, we know that the formula of volume of a cylinder is pi r squared h, where h is the height of the cylinder, which in this case is 1, but we don't know the radius. We just know that the circumference is 6. So formula for circumference is 2 pi r, that is 6, which means r equal to 6 by 2 pi or 3 by pi. Now substituting this radius over here, we get pi 3 by pi the whole square into h, which is 1. So we get 9 by pi. And the volume of this particular cube will be, as we know, side cube, but all its sides are of 1 unit each. So it will be 1 cube equal to 1. Hence the ratio of their volumes is 9 by pi upon 1 or 9 by pi itself, which is option C. That is our answer. This is a mathematical aptitude question based upon profit and loss. We have been given details about two items P and Q in this table. They are saying that the ratio of the cost price of item P to item Q is 3 by 4, which means we have P by Q equal to 3 by 4 equal to 5400 upon X, because we already know the price of P but we don't know that of Q. So we find out X as 4 by 3 times of 5400 and we get that as 7200. So that is the selling price of object Q. So we write that over here. Discount is calculated as the difference between marked price and the selling price. So we have been given the marked price but we do not know what the selling price is. So we will use the profit percent to find out the selling price. We know that profit percent is selling price minus cost price, which is this one, upon cost price into 100. So we know that there is a 25% profit on item Q. Hence we can write that 25 equal to selling price of Q minus its cost price, which is 7200, upon the cost price, which is 7200, and that into 100 times. So solving this, we get 4 times over here. So SP minus 7200 equal to, we shall cancel out this, 4 ones, 4 eights and 1800. So we get the selling price of Q as 9000 rupees. So we write that selling price as 9000, its marked price has been given as 10,000 rupees, which means the discount given is 1000. So if an item has been marked with 10,000 rupees and it has been sold for 9,000 rupees with a discount of 1000, means this is a 10% discount. Discount percentage equal to 10. How do we calculate that? 10,000 minus 9,000 upon 10,000 into 100, same way as we did for profit. So this becomes a 10% discount. That will be our answer. This is a probability based question. We have been given 5 bags, each containing identical sets of 10 distinct chocolates, which basically means we have these 5 bags. Let us call them 1, 2, 3, 4 and 5. Each of these bags has 10 distinct chocolates and we have to draw one chocolate from each of these bags. The probability that at least 2 chocolates are identical is to be found out. So now for this case, if we want at least 2 of them to be identical, then we can first of all take out that case in which we have all possibilities, which can include every possible choice of chocolates from these bags. In that case, we can have identical, we can have distinct, all are included. And from that, we subtract the case in which all the chocolates drawn will be distinct. So for this, after subtraction, we will be left with that case in which at least 2 of them will be identical. So for all possibilities, we will have 10 choices for bag 1, 10 for bag 2 and so on. So that will give us 10 power 5. And for all the distinct case, we have 10 choices for bag 1. Now coming to bag 2, we will leave out the chocolate which has been already drawn from bag 1 and later on we have 9 choices. Now for the bag 3, we will skip those 2 chocolates which have already been drawn from the bags 1 and 2. So we are left with 8 choices. Similarly 7 and 6 choices respectively. So this comes out to be 30240. So we subtract these two cases to get the feasible number of cases as 10 power 5 minus 30240, which is 69760. And hence the probability will become 69760 upon 10 power 5, which was the total number of cases. So we get the probability as 0.6976. That is our answer, option C. This is a syllogism based question. We have been given 2 statements and based upon that we need to determine which of these conclusions hold true. Statement 1 is saying that all bacteria are microorganisms. So we can draw a Venn diagram like this for this particular statement. Bacteria lying inside the microorganism. Now statement 2 is saying that all pathogens are microorganisms. So now these pathogens may lie either over here, or they might intersect like this, or they might lie outside the bacteria like this. All are the different possibilities. Now let us look at these conclusions and try to find counter examples for them to either prove them incorrect, or at the end, if we are not able to find any counter example, then we shall say that the statement is correct. Let us look at the conclusion 1. Some pathogens are bacteria. Now it is possible that those pathogens are lying in this particular region. So by being here, they are microorganisms, but they are not bacteria. So we have found a counter example that it is not necessary for the pathogens to be bacteria. They can still be microorganisms. So this statement is incorrect. The conclusion 1 is false. This one is saying that all pathogens are not bacteria. Again, this is not necessary because the pathogens may be lying over here. In this case, they are all bacteria and they are microorganism definitely. So again, we have found the counter example that it is not necessary that pathogens cannot be bacteria. They can be bacteria or they cannot be bacteria, or only some of them can be bacteria. All are the possibilities. We cannot draw one concrete solution for this. Hence, we cannot say that any of these conclusions can hold true for sure. Both of them are ambiguous. Hence, we shall say that neither conclusion 1 nor 2 is correct. We will go with option D. That is our answer. This is a passage based question. We have been given this small passage and based upon that we need to determine which of these 4 conclusions can be drawn. The passage is saying that some people suggest anti-obesity measures called as AOM, such as displaying calorie information in the restaurant menus. Such measures sidestep addressing the root cause of the problem which causes obesity, and that is inequality between poverty and income. So the passage is giving us an idea that there is a problem called obesity and its root cause is inequality between poverty and income. But some people are suggesting a measure called as AOM, anti-obesity measure, to curb this problem, and that measure is saying that we should display the calorie information in the restaurant menus, whereby they might be thinking that people eating at the restaurant would be prevented from consuming extra calories, and that would help us in reducing the obesity in the longer run. While this might be helpful, but it is not addressing the root cause of the problem directly. So let us look at the options and try to determine which can be drawn from this. The proposed AOM addresses the core problem that causes obesity. No, it is not addressing the core problem, because the core problem is the inequality between poverty and income. So it is like just treating the symptoms without looking at the actual cause of the problem. So that is incorrect. If obesity reduces, poverty will naturally reduce, since obesity causes poverty. Now, while this statement might be correct, but it is not in relation to this passage. It cannot be actually linked and be drawn from this particular passage. So we will say this is also incorrect. AOM are addressing the core problems and are likely to succeed. It might be likely to succeed, but it is not addressing the core problem. It is just treating the symptoms. So again, this option is incorrect. AOM is addressing the problem superficially. Yes, this is correct. It is just treating the symptoms superficially or superficially without addressing the root cause. So the correct statement is D, which can be drawn from this passage. Programming question. We have been given a C code. There is a function called simple function, and it is taking as parameters an integer array, an integer n, and another integer x. It is performing some actions, and we have to determine what would be returned by this function when it is called with these parameters. Z is an array, and 10 and 2 are these corresponding values for n and x. 10 and 2 we have. And what is our array Z? It is an array of 10 elements, such as Z of I is 1, which means it is having the same value 1 for all of its 10 index. So let us write that 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So this is our array Z. Initially all of its elements are just 1. So this is our array Z, which we are passing to this simple function. N and x are defined as integer values with 10 and 2. So let us see what does this function do now. First of all, it is initializing a variable total as y of 0. What is y? Y is the corresponding value for this array which we had passed into that function. So this y of 0 will actually correspond to this element 1. So initially we get total equal to 1. Loop index is another variable which it has defined. Then it runs a for loop where this loop index runs from 1 to less than equal to n minus 1. Now n was 10, so this runs up to 9, which means from 1 till 9 the loop will run. It is incremented by 1 in each step, and what is it doing? It is making total equal to x times of total plus y of loop index. Now what is this x? X is constant, it is always 2. So let us trace out all the 9 iterations it will go through, and let us see what is the value of total that will be returned by this function. So while our loop index is at 1, then what will total become? 2 times of total. It is currently 1, so 2 times of 1 plus of loop index of y of loop index. Now this is our array y and y of 1, which means 1. So in the first iteration, the value of this variable total becomes 3. Now in the next iteration, x times of total, which means 2 times of 3 plus y of loop index. Loop index is always, y of loop index will always give the value 1, because all the elements of this array are 1 itself, and we're not modifying this array at any place. So this will always be 1. That gives us the value 7. In the next iteration, it will be 2 times of 7 plus 1, which means 15. Then in the next time, 2 times of 15 plus 1, that is 31. Then 2 times of 31 plus 1, that is 63. So as you can see, it is taking up all the values which are powers of 2 minus 1. When, let us note down here, when the loop index was 1. Initially it took the value 1, then while the loop index became 1, it took the value 3, then 7, then it took 15, 31, 63, and so on. So we can say that when loop index is L, or let us say K, then the value of total is 2 to the power. As you can see, it is 31 at 4. So in the next time, it will change from 63 to the next power of 2 minus 1. So after 64, actually what do we get? 128. So this will be 127. After that 255, then 512 minus 1. So 511. Then in the next time 1024 minus 1, 1023. So this is actually total is 2 to the power k minus 1 and minus 1. We can check that if value of k is 4, it is 2 to the power k plus 1 minus 1, because when value of k is 4, then it takes 2 to the power 5 minus 1. Similarly, when value of k is 9, then it will be 2 to the power 10 minus 1, which is 1024 minus 1, 1023. So this is the value that will be returned by the simple function when called with these parameters. So answer for this question would be 1023. This is a DBMS question based on relational algebra. We have been given an employee table which is having 500 records. The name of that table is employee age, and it is having two attributes, employee number and their corresponding age. And in this relation, this attribute employee number is the primary key that has been given. And now there is a relational algebra expression over here, and we have to determine what is it actually generating. So as we can see here, we have the rename operation. It is renaming this first attribute employee number as employee number 1 and age attribute as age 1 from the employee age table. So this is the operation that will be performed first. It is simply creating another instance of the same table with renamed attributes, so we can differently identify them. And then from this new table, from this new relation, what they are doing is a join operation is being performed based on this condition. What is it? From the employee age relation, we are extracting those tuples in which the age is greater than age 1. And what is this age 1? Age 1 is ages of all the employees in this new relation. So this first part of the query is actually filtering out those tuples in which the age is greater than any of the ages present in this new relation. So what will actually happen is, every time we execute this first condition, entire new table will be traversed. And in this new table, if we find any such age 1 and age in which there is such a relation existing between them, for every age we will traverse the entire new table. And if we encounter any age 1 such that age is greater than that, then this tuple will be filtered out. It would be returned to us. And at the end, out of that obtained relation, we are extracting out the employee numbers. So in effect, what this expression is doing is, it is filtering out those employees which are having their age greater than age 1. And what is the age 1? Age 1 is the ages of all the employees present in that relation. So basically what it's trying to do is, it will give us those tuples in which the age of the employee is greater than at least one of the employees, or we can say the minimum aged employee will not be considered. Let us say the ages of the employees are 10, 12, 20. Quite low for the age of an employee, but okay, let us assume that. So now this age 1 will traverse over all of that, and while we are dealing with the first tuple, that is 10, then we will not find any age 1 value such that 10 is greater than that. So this tuple will not be taken. Then we'll move to 12, and for that again we are traversing 10 is found to be lesser than 12, so this tuple will be included. Then we move on to 20. Again, we find 10 to be lesser than that, so this will also be included. So we will be taking all those employees which are not having the minimum age, and there can be multiple employees with the minimum age. So we cannot say that employee numbers of only those employees whose age is more than age of exactly 1. This were true if the ages were unique, but we can have multiple employees with the minimum age and all of them will be excluded. Hence, this option C would be correct because we are taking employee numbers of all the employees whose age is not the minimum. So excluding these, we are taking all the others. And at the end there is a projection operation. So from those tuples, we are extracting out the employee numbers only. So this is the result that will be returned by this expression. So correct option is C. This is a computer networks question based on TCP connection establishment. It is saying that a TCP server application is programmed to listen on port P on a host S. P is the port number and S is the host they are talking about. A TCP client is connected to the server over the network. Means a connection has already been established between them using port number as P. Now consider that while the TCP connection was active, the server machine S crashed and rebooted. So while the connection was already in place, in between that the server instantaneously crashed and it had to be rebooted. Now assuming that the client does not use the TCP keep alive timer, what is this timer used for? It is used by a client to know how long to keep that connection active and when to close that connection. If that timer is not used, then it will not know about the state of the server, if it is listening, if at all or not. Then in this such a scenario, what are the possible behaviors that has been asked? Option A is saying that if the client was waiting to receive a packet, then it will wait indefinitely. Now the server has crashed and rebooted, so it will not remember that what all open connections it was having before the crash. It has lost its memory. Also, the sender or the client is not keeping this keep alive timer, so it will keep its connection on for as long as it does not receive back from the server. But now the server is not going to send any packet or any such message to the client that it had rebooted or anything like that. So now the client has no other option but to keep waiting indefinitely, waiting for the server to respond, which it is not going to. If it had this keep alive timer, then it would have waited for a finite amount of time and then it would have closed the connection itself. But that is not going to happen in this case. It will keep on waiting in an infinite loop. So option A is true. And this was an MSQ type question, so multiple would be correct. B is saying the TCP server application on S can listen on port P after the reboot. Now, it was initially listening on port P, then that connection got terminated and it had to reboot. It was not a proper termination. That connection had just simply crashed and then it rebooted. So after rebooting, it is possible for the server to once again listen at the same port because it is now not aware of what port it was listening prior. So all the ports have an equal probability of being chosen. So even the previous port P can be chosen for establishing the new connection now. So B is also a possible scenario. Then C is saying if the client sends a packet after the server reboot, then it will receive a RST, which means reset segment. Now the connection has terminated, it no longer exists. The server does not remember what all connections it previously had. And in such a scenario, the client is unaware of this thing. So it tries to send the packet to the server, assuming that the connection is still in place, it is still intact. So this client tries to send a packet to that server. But now what the server will do? It would say there is no connection. How can I receive your packet? So it will attempt to reset the connection by sending this RST segment. So option C is also true. The last one is saying if the client sends a packet after the reboot, then it will receive a FIN segment. Now, when do we use this fin segment? It is used for the connection termination. If in the first place there is no connection at all, then what are we trying to terminate? The server would say there is no connection, then why should I send the fin segment and try to terminate it? It will simply attempt to reset or re-establish a new connection with the client instead of trying to terminate a non-existing connection. So fin will not be sent out. So option D is incorrect. The correct options are A, B and C, and that is our answer. Pilot design question in which a C code has been given for which we have to construct a directed acyclic graph DAG. This is used in compilers for the intermediate code generation and the code optimization processes. So the reason being that it minimizes the number of nodes we require if we had instead constructed the usual symbol tree like of notation. So let us see what is the number of nodes this DAG will have when we construct it for the given C code. The first statement given is A equal to B plus C, so that can be represented as this. Let us call these two nodes as B and C, and we are performing the plus operation on them, so that can be represented here, and this node will correspond to A. Then in the next step they are saying E equal to A plus 1. So now we already have node A over here. So this is the plus operation that resembles E, and here we have 1. Then D equal to B plus C. We have both B as well as C. B plus C, the result we have already there stored in this node, which is currently A. So D will also be assigned to the same node. Then next is F equal to D plus 1. Again D is here, and that plus 1, that result is stored in this node, which is currently resembling E. So F will also point to the same node. Finally, G equal to E plus F. Now E and F are both these same node. So if we have to store their sum, then we just need one more node. Let us call that G, E plus F, and both the branches will be pointing to the same node itself. Reason being, both are actually the same node, so their addition will be performed on that itself, and the result will be stored in this node G. So this is the DAG for the given C code we have got. What is the number of nodes we used? It is 6. Instead, if we had constructed the usual symbol tree, it would have taken more number of nodes. So that is the advantage of this, and the answer we got is 6. This is a calculus question. We have a limit to be evaluated on this function for the variable x tending to -3. So let us first check out what is the indeterminate form existing in this function. For x tending to -3, the numerator would assume the value 2 times of -3, which is -6, and that plus 22 gives root of 16 minus 4, so that tends to 0. Similarly, the denominator is -3 plus 3, so that also tends to 0. Hence, this is a 0 by 0 form, and for such cases of limit, we can go for the L'Hospital rule instead of going for the traditional method that would be longer. So with L'Hospital, we can get the quick result. And what do we do in that? We separately differentiate the numerator and the denominator until the indeterminate form is removed, and after that we substitute the value for the given variable. So here the numerator is 2x plus 22 minus 4. When we differentiate this with respect to x, it would be something like d by dx of this numerator. That will give us, now this for root symbol, it is 2x plus 22 to the power half. When we differentiate this, it would be, this power would come ahead, that would become 2x plus 22, and to the power we reduce it by 1, so that would be minus half, which means 1 by 2x plus 22. And now since this is 2x, that when differentiated would give us a 2, and for 4 it would be simply 0. Similarly, when we do for the denominator, it will be d by dx of x plus 3, that will give us 1. Now here these 2 get cancelled out, and we are simply left with 1 by 2x plus 22. Now here we do not have any indeterminate form, so we can simply substitute the value of x equal to -3, and that would be the result of our limit. So this gives us 1 by root of 2 times of -3 plus 22, which is 1 by root 16. That gives us 1 by 4. That is the answer for this limit. And we have to express it in rounded off form up to 2 decimal places. So we'll be reporting 0.25 as our answer. DSA question based on hashing. We are considering a dynamic hashing approach for 4-bit integer keys. These are the given conditions which specify how the hashing is exactly done. There is a main hash table of size 4. So we have a hash table only of size 4, not greater than that. And how the hashing is done, there is no proper hash function as we are aware of. They are stating a custom built hash function based upon which it is to be done. The 2 least significant bits of a key is used to index into the main hash table. Now our integers are 4 bits. Let us call that I3, I2, I1, I0. So I1 and I0 will be used for hashing. It is a of size 4 hash table, so it will have the index as 0, 0, 0, 1, 1, 0 and 1, 1. These are the corresponding values of this I1 and I0. Next, initially it is empty. Thereafter, when more keys are hashed into it, then to resolve the collisions, the set of all keys corresponding to a main hash table entry is organized as a binary tree that grows on demand. Now, what mechanisms are we aware of in order to resolve the collision? We know of a linked list approach in which there is a hash table like that. It has limited space, and when that is filled, we use this chaining kind of thing. A linked list is built over here. We have to traverse that entire list in order to search for an element. This is the main hash table, which is limited in size, and then if there are any collisions, then all those elements are placed into a linked list kind of structure. So the same thing is given over here in a slightly modified way. Instead of linked list, they are using a binary tree which grows on demand. How does it exactly grow? Let us see. First, the third least significant bit, which means this I2, that is used to divide the keys into left and the right subtrees, which means if I2 is 0, then we'll go left. If it is 1, then we'll go right. That way the binary tree will grow. To resolve more collisions, then each node of the binary tree is further subdivided into left and right subtrees based on the fourth least significant bit, which means, let us say, we have two numbers, their LSBs are 1, 1, their MSBs are 0, 0, and their I3, which is the most significant bit, is 1 and 0 respectively. Then using these two, they will be mapped to the same index. Now it causes a collision, so we'll look for the I2 bit. Now again it is causing the collision. So since it is 0, we'll be moving left. This is how the tree will grow. But now since again there is a collision, then while inserting this next key, we'll check for the most significant bit, which is I3. Now it is 1 for this and it is 0 for this. So accordingly the tree will be grown. From this branch will go out like this, 0 and 1. This is for 0, this one is for 1. So that is how the tree will grow. Split is done only if it is needed, only when there is a collision. So using this given information, we have to identify which of the given sequence of keys when inserted will cause such a hash table to be formed. That has been given to us in this diagram. So let us take each example one by one and see what happens. The first one is 10, 9, 6, 7, 5, 13. So let us first write down their binary representations. For 10, it will be 1, 0, 1, 0. 9 will be 1, 0, 0, 1. You have to take 4 bit in all of them. This one will be 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1. This one is 8. So 8 plus 4, 12, and plus 1, 13. So we've got the binary representation of all of them, and we are inserting them in the same order, starting from 10 up to 13. So when 10 is inserted, it would be inserted in this index 1, 0. Here we are inserting 10. As of now, initially it is empty, so there is no collision. Then next, for inserting 9, 0, 1. So here that 9 is placed. Then for 6, 1, 0. So it is a collision now because that slot is not empty, 10 is already there. So now we will have to check for the I2 bit. For 10 it was 0 and for 6 it is 1. So now this will have to be grown 0 and 1. Then on this side, this side will resemble 10 and this side will resemble 6. So both are inserted. Next, 7 over here. Then for 5, 0, 1. Again there is a collision because 9 is there. So we will check the third bit or the bit I2. In case of 9, it is 0. And in case of 5, it is 1. So this will be grown like this, 0 and 1. And what does 0 represent? This is 9 and this one is resembling 5. So fine till now. Then we have to insert this 13. Again we see from the last two bits there is a collision. 9 and 5 are both there in the slot. 10 and 6 are there in the slot. So there is a collision for 13 as well. We will check the I2 bit, which is 1. And we see that this tree is already having a branch at 1 like this. 5 is currently there at that branch. So it again makes a collision. So now we will have to check for the MSB for the I3 bit. And what did it collide with? With 5. So for 5, the MSB is 0. And for 13, the MSB is 1. So we will grow that tree from here. The 0 side will represent 5 and this 1 side will represent 13. So that is how 13 is also inserted in this slot. So as we can see from option A, we have got the same structure of this hash table as we were expecting. So this is a correct option. Let us also check for some other option and see if we can get the same. A is true. Let us check for, let's say, option C. You can check for all of them, but this was an MCQ question, so there is no need to check all the options. If we have got one to be true, then that can be reported as the correct answer. But just for understanding, let us also check option C. Now it has 9, 5, 10, 6, 7 and 1. So we'll write the binaries 1001, 0101, 1010, 0110, 0111, 0001. This is the sequence in which they will be inserted. So starting with 901, so it will be placed here. For 5, again it is 01, there is a collision. So checking the third bit or the I2 bit, 0 and 1. 0 side will grow the tree like this on both sides. 0 side will represent 9. 1 side will represent 5. Both are inserted. Next is 10. 10 is inserted. 10 again. 6 has to be inserted. There is a collision now. Then we'll grow the tree. 0 side will represent 10. 1 side will represent 6. Both are inserted. Next we have 7 to be inserted here. Finally we have 1 in 0, 1. And there are already 9 and 5 both over there. So 9, 5 and 1, all three collide. We check for the bit I2, which is 0 in this case. And for 9 also it was 0. So now there is a collision between 9 and 1 from this 0 side. So now the tree will have to be grown like this, 0 and 1. Then that 0 side will represent 9. And as we can see, both of them are having 0 over there. So we are again checking their most significant bit, which is 1 here and 0 here. So the 0 side now will represent 1 and this 1 side will represent 9. So this branch is not there. We had to grow the tree from zero side. So there is a different structure we are getting out of this. And similarly, we can also check for the options B and D, and we'll find out that only option A will give us the hash table which is mentioned over here. So that is the correct answer. This is a mathematical logics question. We have been given P and Q as the two propositions, and based upon that, we have these S1 and S2, which we have to be determined if they are tautologies or not. So now, one thing we'll be using over here is that if there is an implication such as X implies Y, then that can be converted into X bar plus of Y. So this thing will be applied for simplifying the given propositional statements to us. The first one is not of P. Okay, now here we can convert this and or operation into and will convert into dot and or will convert into a plus. Others will remain same and implication will be turned into this particular like Boolean operations we are making out of it. So S1 will turn into P bar and P or Q, and we'll be taking the whole bar plus of Q, the antecedent and precedent parts, or as we say consequent or subsequent parts. The left side will be taken complement of, and implication would turn into OR operation, while right side will remain the same. Now when we go to simplify this using De Morgan's law, it gives us P and converts into OR, and then this is P plus Q, the whole bar, and plus Q. Then that converts into P plus, again applying the De Morgan's law over it, it is P bar Q bar plus of Q. Then we apply distributive law on this, OR is distributed over AND. So that gives P plus P bar, P plus Q bar plus of Q. Now this P plus P bar, it is 1. So we are just left with P plus Q bar plus Q. Again this Q and Q bar will give 1. So we are just left with P plus 1, which is 1. Or we can say true. So because this S1 resulted into true, we can say it is a tautology. Now let us also check for S2. Applying the same thing, the left side will be taken complement of, and implication turns into OR operation. The right side is P bar AND of P or Q. So this becomes Q bar plus this P bar into P or AND P plus of P bar and Q. So this converts into P and P bar cancel out, giving 0. So we just have Q bar plus P bar into Q. Now again applying distributive law on this, it would give Q bar plus P bar ANDed with Q bar plus Q. This Q and Q bar will result into 1. So we are just left with P bar plus Q bar, which cannot be further simplified. So we can say that it is not a tautology, and there is no other option such as contradiction or anything unless we know the values of P and Q. So this is the only resulting expression we can arrive at. So we'll simply say that this S2 is not a tautology, and S1 we have already arrived at conclusion that it is a tautology. So the correct option we can go with is S1 is a tautology, but S2 is not a tautology. So the correct choice would be B. A DSA question based upon stacks and queues. We have been given the following set of operations that are performed on an empty stack. Let us see what is the result of that. This is our stack. Initially it is empty. The first operation is push 54 into the stack. Then we push 52 into it. And after that the next operation is pop. So this 52 will be popped off from the stack. Next we push 55. Then we push 62, and finally S equal to pop. The pop returns the topmost digit which has been popped off from the stack. In this particular call, we did not return the value from this pop. We did not hold that value returned by this pop, but here we are holding that value in this variable S. So S will retain this value of the popped element 62. It will be popped off, and the stack which is now left out is it is having elements 54 and 55 only. So we are done with the stack operations. Now an empty queue has been given, and on that we are performing this set of operations. So let us see. This is our queue, NQ21. So we enqueue that from this end. Then we are NQing 24. We are NQing from this end and we'll DQ from this end. So 24 is NQ'd. Then we are doing DQ. Again, the value returned is not being held. So this 21 will simply be removed. Next operation is NQ28. So from the rear end, we are entering this value 28 into the queue. After that, NQ32. And finally, Q equal to DQ means the value which is at the front of the queue will now be deleted, and that would be held in this variable Q. So this Q will be holding this value 24, and our resulting Q will just have elements 28 and 32. So now the variable S is holding value 62 and variable Q is holding the value 24. And we have been asked the value of S plus Q. So that would simply be 62 plus 24, which is 86. So the answer for this question is simply 86. Electronics question based on number systems representation. We have been given the IEEE 754 single precision floating point format with a bias of 127. The sign bit, exponent bit, and the fractional part, or you can say the mantissa, has been given to us, the 32-bit representation. And we need to determine the value of the floating point number denoted in this format. Up to 2 decimal places, the result has to be rounded off. So let us see. We'll be following the implicit normalization form, and bias is already given to us as 127. So the result would be the sign bit minus 1 raised to the sign bit into 1 point, since we are using the implicit normalization. So 1 point mantissa, which is this bits, and it starts from this side, from left to right instead of right to left, and that into 2 to the power exponent. Exponent is the one which is given to us minus bias, which means minus of 127. This would be the resulting value. Let us compute what it turns out to be. Minus 1 raised to S. S is the sign bit, it is set to 1. So here it will be 1. The result would be a negative number. Into 1 point mantissa. What is mantissa? First 4 bits are 1 and rest all of them are 0. In total this would be 23 bits. This is 1 bit and this is 8 bits. In total they make up 32 bits. So from these 23 bits, just first 4 are 1s, rest all are 0s. So we can just write it up to this point. There is no need to write any zeros because anyway they do not have any value. And hence now we can go for the exponent part, which would be 2 to the power. Now this exponent, it is an 8-bit number whose value we can check to be, this is the last bit 128 it corresponds to, and this is corresponding to 1. So this number is 129, and from that we will be subtracting the bias, which is 127. So result is 2. And now when we go to evaluate this is minus 1 into 1 point followed by 4 ones, and then we have 2 in the exponent part, which means this can be shifted, this decimal point can be shifted 2 places ahead. That would become 111.11 because this point has been shifted to this place and to this place. 2 places have been shifted because of this exponent. Hence this is our result. Now we can simply convert this into decimal and see what it is. The result would be negative, hence the minus sign, and when we convert this number to negative 111.11, here we use the usual weights, 2 to the power 0, 2 to the power 1, 2 to the power 2, and on this side we use the weights as 2 to the power minus 1, 2 to the power minus 2, that way. So result is 1 times of 2 squared, which is 4, plus 1 times of 2 plus 1 times of 1 plus on this side 1 times of 2 to the power minus 1 means half plus 1 by 4. This becomes 4 plus 2 6 plus 1 7 plus half and 1 by 4, so 3 by 4. That becomes 7.75, and the result will be negative. Hence the answer for this question is minus of 7.75. It was a numerical type question, so this is the answer that has to be reported, and it is already having just 2 decimal places, so there is no need to further optimize it or round it off. This can be entered as the correct answer. This is a digital logic question based upon number system. They are talking about a number whose representation in base 3 is 210. And we want to find out what would be the hexadecimal representation of that number. Let us say that number is x in the decimal system and its equivalent number in base 3 is 210. And what we need to find out is its hexadecimal equivalent. So for this, it would be better if we first find this number itself and then convert it into its hexadecimal form. So how do we do that? We convert this number in base 3 into base 10. And for that, we will simply multiply this given number with the powers of 3 according to their weights. That would become 2 times of 3 squared plus 1 times 3 plus 0, which becomes 18 plus 3, which is 21. So our number x is 21 in base 10. So now we can convert this number 21 into its hexadecimal equivalent. And for doing that, we can simply subtract 16 from it. 21 minus 16 gives us 5, and that 1 will be here. So it becomes equivalent of 15 in hexadecimal. So the correct answer for this question would be A, 15. ABMS question based on transactions. The Ri and Wi are defined as the read and write operations performed on an attribute Z, and I represents the transaction name, which is Ti. Now we are given two schedules S1 and S2, and we have to determine which of them is or are conflict serializable. So let us write down these schedules in the tabular form. S1 can be written as, there are just two transactions involved, T1 and T2. So we create a table like this. We have to find out what all dependencies are existing between those data items. So as you can see, the first operation given is read 1 of x, which means transaction 1 is performing a read operation on x. So this way. Next is read 1 on y. Transaction 1 is reading data item y. Then read 2 of x. This is reading x. Then read 2 of y. Then write 2 of y, followed by write 1 of x. So this is the schedule, and let us now find out what all the dependencies existing. As we can see here, a write is performed on y, and in T1 read is performed. So this is one dependency we have from T1 to T2, and as we can see here, the write is performed on x, T2 is reading on x. So this is also a dependency, and this dependency is from T2 to T1. So if we go on to make a graphical representation of this, then there will be a loop formed in that, and hence it suggests that S1 is not conflict serializable. Now let us check the S2 schedule. Again, it is having just two transactions, T1 and T2. So we can create the table for it in the same way. The first operation given is read 1 on x. So T1 is reading a data item x. Next is read 2 of x. X is being read by T2. After that, we read 2 on y. Then write on y by T2, followed by read on y by T1. Finally, write x by T1. Now here, let's find the dependencies. We have a write operation on y, and as we know, there are just two types of dependencies. One is write write and one is write read or read write. If both the transactions are reading, then this read read dependency is not a conflicting dependency, we can say. It does not cause any conflict. It is possible for many transactions to read the data item at the same time. But if any one of them is writing it and then the other is reading it, or if the other one is writing it, then it would cause a conflict. So here, what are the conflicting operations we have? This is write on y. Then do we have any read or write operation on y in T1? Yes, here we have. This is a dependency from T2 to T1. Then in T1, we have a write on x. Do we have any operation on x in T2? Yes, here we have read on x. So this is also a dependency, and it is again from T2 to T1. So for this, the dependency graph would be just like this. There is no loop in that. So we'll say that this S2 is indeed conflict serializable. So correct option would be B. S1 is not conflict serializable, but S2 is. So we'll go with option B. A probability question. We have a sender S and a receiver R which are following a transmission using two different types of signals H and L. A sender can send either of these two signals to the receiver and receiver will interpret what it has received. Now the probability of the sender sending a signal H is 0.1 and sending L is 0.9. So let us note down these probabilities. Probability of sending H. S means sender, the signal has been sent, and which signal was sent? H. So this probability is 0.1 and probability of sending L is 0.9. Next, in the graph below, the weight of an edge u, v is the probability of receiving v when u is transmitted, and both these uv belong to H and L set. So now let us consider this H. It's our sender side and the receiver side. HL, two types of signal which it can send, HL which it can receive. Now, as we can see in this graph, it is possible for the receiver to misinterpret a signal. When H was sent, it can receive H, it can also receive L, which means it can misinterpret the received signal to be H or L, irrespective of what it originally was. The probabilities of happening such things are given in this graph. So now if we consider this particular edge, this edge. Now this is edge u, v, and what it is said, the edge u, v represents the probability of receiving v when u is transmitted, means probability of receiving L when H was transmitted. This is what that edge is representing, and probability is given as the weight of that edge, which is 0.7. Similarly, the other edges, this one is probability of receiving H when L was sent. It's 0.8. For this one, probability of receiving H given that sent was also H, it is 0.3. The last one, probability of receiving L given that L was sent, is point. This one we are dealing with LL 0.3. So that is all the information given to us. Now what is asked to us is, if the received signal is H, which means probability of, let us read it completely, the probability that the transmitted signal was H. We have to find out the probability that the transmitted or the sent signal was H, given that the received is H. It is given that H has been received. Then what is the probability that H itself was sent? Isn't it 0.3? Simply looking at this branch. No, it's not. This branch is representing the probability that H was received given that H was sent. This is the reverse of that. We want probability that H was sent given that H was received. So both are different, but they are closely related. We can derive one from the other. How do we do that? We can write this one as, using the Bayes theorem, can write it as probability of sent H intersection received H upon probability of receiving H, and we can further simplify it as, the numerator is, it can be written as probability of receiving H given that sent was H multiplied by probability of, now as we know we can write an event as, let us say, probability of A intersection B, it can be this when divided by probability of B is equivalent to probability of A given B. So if we want this intersection, then we can write it this way. The numerator can be written as this: receiving H given that sent was H multiplied by probability of sending H upon the denominator is probability of receiving H. So now we have to calculate this thing. How do we do that? This value we already know, it is 0.3. What is the probability of sending H? 0.1 from here. Now we want this one, probability of receiving H. We don't know that already, so we'll also have to compute it. And how do we do that? And there are two cases in which we can receive H. It will be probability of receiving H given that H itself was sent, and probability of receiving H given that L was sent. So that can be written as, it will be probability of receiving H given that H itself was sent, and this will be multiplied with probability of. Now we are using the Bayes theorem to divide this into two different cases. For receiving H, there are two cases. Here we are dealing with the first one, receiving H given that H itself was sent. So here we will have it this way, means we sent H, and then given that we sent H, what is the probability that we'll receive H? Same way the second case would be probability of receiving H given that L was sent multiplied with probability of sending L. So here we sent L, and then probability of receiving H given that L was sent. So this is what will give us the denominator value. Let us calculate it. This we already know is 0.3. Sending H is 0.1 plus of this also we already know, it is 0.8, and for sending L it is 0.9. So we calculate that. Let us do it on this side. Yeah, on the left we have some space. So this will be 0.03 plus 0.72 equal to 0.75. So this is our denominator. And what about the numerator? It is 0.3 into 0.1, which is 0.03. So we compute this. The numerator 0.03, denominator is 0.75. So removing the decimal point, it becomes 3 by 75. You can cancel it out to get 3 twice 6 and 3 5s 15. So it is 1 by 25. But we want it rounded off to 2 decimal places. So this will become 0. We take 1 0, not divisible, 0, 1 more 0, 4, 25 4s 100. So we get the result as 0.04. It was a conditional probability question using Bayes theorem. We have solved it, and answer we got is 0.04. This is a graph theory question. We have been given a graph G, which is undirected, connected, and planar. For such a graph G, it has 8 vertices and 5 faces. Then what would be the number of edges in this graph? So first of all, you have to be convinced whether this graph would have a fixed number of edges or not. For that, you can try constructing some graphs and check it out. But here, since it is given to be undirected, connected, and planar, we can directly apply the Euler's formula in such a graph. It will hold true when the graph has these properties. So applying the Euler's formula directly, which is V plus F minus E, it is an identity which results into 2, where V is the number of vertices, F is the number of faces, and E is the number of edges. This identity gives us the value 2. So using this identity, now we can substitute the values and find out the answer. And how do we know whether it will hold? Because there are certain conditions that this graph has to be undirected, connected, and planar. Then it would be following the Euler's formula. So for this graph, we simply get, in place of V, we can substitute 8, then 5 faces, edges are to be found out, equal to 2. So we get 13 minus E equal to 2, which means this graph would have 11 edges. So you can try constructing such a graph. It will always have 11 edges, however you make it. There are no multiple answers possible for this question. It will simply be 11. This is an algorithms question based on asymptotic notations. We have been given 3 functions, f1, f2, and f3, defined in the terms of n. All of them resemble some kind of exponential function. We basically have to arrange them in the increasing order of their asymptotic growth rate. So now we cannot directly compare these functions. Let us try to take log of each of them and then substitute some value of n, some large value, to be able to compare them easily. So when we take log of each one of them, then this f1 converts into log of 10 to the power n, and we're taking the base to be 10 itself. So this becomes n times of log 10 to the base 10, which is n itself. So f1, log of f1 actually becomes n. And if we compare the log of f1, f2, f3, and then that relation would be still holding true for f1, f2, f3 itself. So it does not matter if we are comparing the functions itself or their logs. And hence we are converting them into their logs so that it becomes easy for us to compare. Then this f2 would become log of n to the power log n. Then this log n can be brought outside. This becomes log n of log n. So basically log n squared. Log n the whole squared. Coming to f3, that becomes log of n to the power root n. Root n will come out. So it becomes root n times log of n. Root n log n. Alright, now let us substitute some value of n. Then it would be easier for us to compare, or we can even directly look at it that okay, let's substitute, then it would be easier. Some large value of n, let us say 10 to the power something 50, that would do. So when we substitute that value of n, then this log of f1, which was n, that converts into 10 to the power 50. Then this f2 is log of n and squared of that. So what does log of 10 to the power 50 become? It is simply 50. So this becomes 50 squared, which is not very huge. So from here we can see that f1 is greater than f2 asymptotically. Let us also check f3. It is root of n, means root of 10 to the power 50, that can be 10 to the power 25, and that multiplied with log of n, which we just saw, is 50. Now we can compare these three easily. It can be seen that f1 is the biggest of them because it is 10 to the power 50. So that will come first in the decreasing order I'm talking about. Then after that, this f3 would be second and this will be third, 50 squared. So there, in the increasing order, they will turn out to be f2, f3 and then f1. That is their increasing asymptotic growth order. So we'll be going with option D. This is a TOC question from pushdown automatas. We have been given a PDA defined using the standard definition, and the transition in this PDA has been defined at this way. If P and Q are the two states, then a transition defined in this way. It states that if we currently saw the symbol A and the top of the stack right now is X, then on reading this particular symbol A, the top of the stack will change from X to Y. That is how these transitions are defined. In the usual notation, we use the symbol such as on reading A, if the top of the stack is empty, use this way. On reading A, if the top of the stack is currently empty, then it would be changed to A. That's the usual notation we use. Here they have used a slightly different notation, which states that on reading the symbol A, if the top of the stack is currently X, then it would be modified to Y. Now in this PDA, P and Q belong to the states and all the standard definitions have been given. There is no alteration with that. The stack alphabets have been given as A and B, and this hash is also accepted. Inside the stack alphabet, they have included the hash symbol and the capital A symbol, which means on reading the input variables small a and small b, the stack variables we will be using are this hash and the capital A. Now let us have a look at this PDA, what it is trying to do, which language is it accepting, and then we have to determine what is the number of 100 length strings that this PDA will be accepting. So first of all, looking at this PDA, this is the start state Q0, and what is it doing? If it was initially empty, then it is putting this hash symbol onto the stack. Now what does this imply? We know that there are two different ways in which PDA accepts a language. The first way is acceptance by empty stack, and the second one is acceptance by final state. Now here we saw that this stack has not been left empty. While it was initially empty, they have pushed this hash symbol onto the stack. So this eliminates our possibility of acceptance using empty stack. Now we will only need to accept the language using final state, because after pushing this hash symbol, it will not be popped out at a later stage. So after this, the stack will not be empty anymore. So we'll only have to go with acceptance with a final state. And let us see what language is it trying to accept. Then going into the state Q1, the stack is no more empty, it is containing the hash symbol on the top, if at all it happens so. Now in this state, there are two different transitions possible. If it reads the symbol A and if it reads an epsilon, which means empty. Now if it is reading this alphabet A, then it will stay in the same state and loop on itself, and it will push this capital A onto the stack, which means it will accept all the small a's. Let us say a string of this form. It will accept, it will stay in the same state, and what will be pushed into the stack? This A symbol will be pushed. And now if there are no more a's and we directly see this empty epsilon symbol coming to the picture, then it will do nothing. The top of the stack will remain the same. Now here, why are they using the epsilon symbol and not the hash symbol? Because it is just to ensure that there is no acceptance using an empty stack. It does not have any other actual significance. We'll simply be dealing with this epsilon to denote that the stack is empty except this A character. So there is, if anything apart from this, they are simply denoting it using the epsilon symbol. So from the state Q1, if we don't see any A's, if we directly see this empty symbol, epsilon symbol, then we'll go into the state Q2. Otherwise, the second possibility is that after accepting all of these A's, whatever the number of A's were there, then after accepting them all, then we are proceeding further. After accepting this, then we are proceeding to the next set of symbols. So in both of these two cases, we'll be moving to this state Q2. And now what are we doing in this state? Here, if we read a symbol small b, then what are they doing? They are popping out this capital A, which means they are essentially popping out this A's against these B's. So if we see any number of small b's, then the same number of A's will be popped out. So it is something like this. For b's, equal number of A's will be popped out in this state Q2. And after that, what happens? Then we go to this transition, and here what we are doing is, on reading this epsilon, what is happening? If there is any capital A left out, then that will remain the same, and we'll go to this final state, which is the accepting state. Which means if after all the B's have completed, if any A is still left into this stack, the hash is there at the bottom, and if any A is left out, then only we will be moving to this final state, otherwise we won't. So that simply means this is not the language we are accepting equal number of A's and B's, because if this happens, then there will be no more A left onto the stack. All the A's will be over. But A should be left. Then only we will be able to accept that language. So this implies that the language we are basically accepting is something of the form A raised to N, B raised to M, where N is greater than M, which means there have to be more A's than B's. Then only an A will be left out onto the stack, and then we will go to the final state. Now, how many A's have to be left out? Just a single A, or any number of A's will be allowed? Any number of A's will be allowed, because we are simply checking if there is any A left out. We are not checking how many are actually left out. There is no loop in this state. So if at least one A is still left onto the stack, then we are simply moving to the final state Q3. So this is the language they are accepting, that there have to be more A's than B's. And we are not concerned with how many more. So now this is the language being accepted by this PDA, and now let us try to answer the question which was asked, that how many strings of length 100 will be accepted by it. So now we know what is the language it is accepting, A raised to N, B raised to M, where N is greater than M. But now the condition is the length has to be 100. So that puts another constraint in place, which is M plus N has to be 100. So now using both of these constraints, let us see what are the strings this PDA can accept. The first condition we can have is N is 100 and B is, or M is 0. So this is possible. Then A 99, B 1, this is possible. Now, is this string really possible? Let us check out. From state Q0, we are always going into the state Q1. Then in the state Q1, if there are no A's, then this transition will be skipped and we'll directly move into the state Q2 using this empty transition. And here again, if there is no B coming, then we'll simply skip this and go to the state Q3. Now here, the main thing is being performed. We are checking if there are any A's onto the stack. If yes, then accept. So this simply states that if there are 0 B's, then also it is fine. So in the same way, A98, B2, so on, until we can have A51, B49. Then after this, A50, B50 will not be allowed because N has to be greater than M. So these are all the possible strings that can be accepted by this PDA. So how many such strings we got? From 51 till 100. So that becomes 50. So there are 50 strings of length 100 that can be accepted by the given PDA. So the answer for this question will be 50. This is a compiler design question about the grammars. Two statements have been given, and out of them we have to determine which of them is or are correct. The first one, S1, is saying that every SLR1 grammar is unambiguous, but there are certain unambiguous grammars that are not SLR1. In order to solve this question, we can take help of the Venn diagram of the languages, which we know is like this. Initially, we have LL0. Then after that, we have SLR1. After that, there is LLR1. Finally, there is CLR1. So that is the Venn diagram. And in this, we know that the grammar can either be ambiguous or it can be unambiguous. So this box, let us represent unambiguous grammar. All of that come under this. And there is a separate partition for the ambiguous grammar. And so from this diagram, we can see here we have the SLR1 grammar, and every SLR1 grammar is definitely unambiguous. Every SLR1 is unambiguous. So part 1 of the statement is true. Now the second part, every unambiguous grammar is SLR1. That is not true, because even this part is also consisting of an unambiguous grammar, but that is outside the scope of SLR1. So we can say that every unambiguous grammar need not be SLR1, but the vice versa is not true. So there are certain unambiguous grammar that are not SLR1. It is true, and it is where this is the portion where such grammars would lie. So the statement is true. Next one. For any context-free grammar, there is a parser that takes at most n cube time to parse a string of length n. Now, given a string of length n, we have to parse it and we have to determine if it belongs to a context-free grammar or if a context-free grammar can be used to generate that language, to generate a context-free language. For this, we have an algorithm called CYK algorithm that takes order of n cube time to parse a string of length n and then determine if it is possible for a context-free grammar to exist in such a way that this will belong to that particular language. So basically we can parse any string as it is mentioned in this statement. There is an algorithm existing for this purpose, and if it is a context-free grammar, we can parse it and then derive the results. So this statement is also true. So we got both S1 and S2 to be true, hence the correct option would be C. This is a DBMS question based on functional dependencies and the decomposition. We are having a relation R having these attributes P, Q, S, T, X, Y, Z and W. And this is the set of functional dependencies existing on this relation. Now this R is decomposed using these two decomposition schemes D1 and D2, and we have to find out which of these two decomposition schemes would yield us the lossless or the lossy decomposition what it is given, that's to be determined. So in the first decomposition scheme D1, we can see R is decomposed into four subrelations. Let us call them R1, R2, R3 and R4. They are having the attributes PQST, PTX, QY and YZW respectively. So now to begin with, let us first find out the candidate key for this relation R. Then we shall proceed with each of these four. For relation R, we can see using its functional dependencies that only X, YX, Y, ZW, these four attributes are coming on the right hand side. So the leftover PQST would definitely be forming the key. Let us see if their closure is enough or if we need to add some other attribute. This closure gives PQST for sure. Along with that, P can derive X and Y, so that comes. Then Y can derive ZW, so all have been encountered. So we'll say that PQST is the candidate key for relation R. Now coming to these four subrelations, in R1 we are having PQST, that will be the candidate key for itself. Then coming to R2, PTX. Over here, P can derive X, YX and so on. So from this particular decomposition, this FD, we can break it into P derives Y and P derive X separately. So we can say that P derives X, but P cannot derive T. So this PT will collectively form the candidate key. Then coming to QY, direct FD exists, Q derives Y, so Q is the candidate key. Similarly for R4, Y is the key because it can derive ZW. Now as we can see, if we check out the relations R1 and R2, then what is the common attribute they are having? It is PT. PT is the common attribute in both of them, and it forms the candidate key in one of the relations, which is R2. Hence we'll say that the decomposition of R into R1 and R2, this particular part was lossless. So these two can be merged together going backwards. They can be merged together to get a new relation, let us say R5, and it will have the attributes P, Q, S, T and X. Let us have a look at these two, R3 and R4. There the common attribute is Y, and this Y is the candidate key in relation R4. So again these two can be merged with a lossless decomposition, and that would form a new relation, let us say R6, with attributes Q, Y, Z and W. Now looking at these R5 and R6, What are the common attributes? Q is 1 and there is no other common attribute. So now for both of these respectively, we'll need to find out what are the candidate keys in them. So in R6, we know that Q can derive Y and then Y can derive ZW. So Q is the candidate key for relation R6. Hence, Q, which is the common attribute in both of them, is forming the candidate key in one of them. Hence, again, this decomposition will also be lossless. So this R5 and R6 can also be merged together, and this merger will give us the original relation, which was R. Hence, we can say that the decomposition scheme D1 is lossless. Now, in the same way, we shall be evaluating for the decomposition scheme D2, and let us see if that is also lossless. So it is again decomposed into 4 subrelations from R1 to R4. Let us note them down. The attributes they are respectively having is R1 has PQS, then TX, QY and YZW. Finding out the candidate keys for all of them. In R1, we know that PQS itself is a part of candidate key of the original relation. So it is like a prime attribute set. So that entirely will form the candidate key for R1. Then coming to R2, T and X, none of them can derive each other. So that collectively will form the candidate key. Then coming to R3, Q can derive Y, so it is the key. And then for R4, Y is the key. When we attempt to merge them, we can see that there is no common attribute in R1 and R2. So let us check out R1 and R3. Between these two, Q is the common attribute and it is forming the key in one of them, which is R3. So we can see that R1, R3 can be merged together to give a new relation R5, which will have the attributes P, Q, S and Y. Similarly, let us check out if R2 and R4 can be merged together. No, they cannot be because there is no common attribute in them. So if we try to merge R2 and R4 together, then this merger would be lossy. Some attributes would be lost. And what do we mean by attributes being lost? It is possible that some tuples, not actually the attributes, it is possible that some tuples may be eliminated or some extra tuples may be added, which were not there in the original relation. Both of these scenarios are considered under the decomposition being lossy. So this R2 R4 merger cannot be performed. If we could merge R3 and R4 together, that is because they are having the common attribute as Y, then it would be possible, but then R1 would have been left out. So there is no proper combination of these 4 relations in which they can be merged together, leading to a lossless decomposition. And hence we will come to the conclusion that this decomposition scheme R2 is indeed lossy. So we would be going with the decomposition D1 is lossless, but D2 is lossy. And hence the correct outcome for this would be first option. Real mathematics question based upon random variables and their covariance. Now we know that for a random variable x, its variance can be given as, in terms of its expectation, as expectation of x squared minus expectation of x the whole squared, or we can also write this thing as expectation of x minus mu the whole square. And we know that what is mu? Mu is nothing but the expectation of x itself. So this thing can be further written as expectation of x minus expectation of x the whole square. So that is how we write the variance of a random variable x. And in the same way we can write covariance between two variables x and y as expectation of xy minus expectation of x multiplied with expectation of y. And in the same way, when we combine these two things together, then it becomes expectation of x minus mu, or you can say expectation of x, and this thing multiplied with y minus expectation of y. and expectation of this whole thing. So that is how we can mention the covariance of x. So now let us have a look at these two statements and we need to determine which of them is or are correct. In the first statement, we can see that the left hand side is nothing but what we just saw, the formula for covariance. So it is nothing but covariance of x comma y the whole square. That is the left hand side of first statement. And if we try to relate the covariance and the variance, then we have the relation as we know the formula for correlation coefficient, that can be written as r equal to covariance of x comma y upon root over of variance of x variance of y. So if we square this whole equation together, then we get something as r squared variance of x variance of y is same as covariance of x comma y the whole square. And now we know that this correlation coefficient r that lies between -1 and 1. So we can say that if we square that, then r square that will lie between 0 and 1 itself. So if we remove this thing and convert this into an inequality, then that would become covariance of x comma y the whole square is less than or equal to variance of x variance of y. So now using this equation, this inequality, we have to answer the two statements. Now coming back to the statement 1, whose left hand side as we saw is the covariance of x comma y the whole square. And what about its right hand side? It is written as variance of x variance of y, and the inequality used is greater than. So we just saw that it is incorrect. If it were less than or equal to, then we would be considering that. Hence the statement 1 becomes incorrect. Now coming to statement 2, it is saying that covariance of x comma y, it is the same formula which we have just derived. Expectation of x minus e of x, y minus e of y. But the difference here is that they are using the modulo symbol, which is not true because we can have the value of x minus expectation of x to be negative in some cases. And if we take the modulo sign over here, then those cases get disturbed. So this is the correct formula which we had just derived. Instead of modulo symbol, they should use the simple multiplication of the two. So this formula also becomes incorrect. This is not how we calculate the covariance. So both the statements 1 and 2 here are incorrect. And hence we'll be saying that option D is true, saying both S1 and S2 are false. Simply a logical question. We don't need to apply any optimization techniques as such in this. They have defined Rn to be the maximum amount that we can earn by cutting a rod of length n meters into one or more pieces of integer length and selling them. So we basically have a rod of length n and we are cutting them, and at a time we can cut it into 2 or more than 2 pieces as well, and then sell those individual pieces, and as a result we'll obtain some profit, and that is what we are concerned with. So for I greater than 0, let P of I denote the selling price of a rod whose length is I meters. So if we are selling these individual pieces, let us say their lengths are I, J, K, L, all of them will be integers. We can sell those pieces individually, and the prices for selling these individual pieces has been given by this array of prices. P of 1 is 1, P of 2 is 5, which basically means if we are selling a rod whose length is I, then P of I will give us the profit we can earn by selling that piece of rod. So for 1 to 7, 1, 2, 3, 4, 5, 6 and 7, we have been given these 7 values, which means if we sell a rod of any length between 1 to 7, this is the respective profits we can get for those pieces of rods. So now they are asking us which of the following statements is or are correct about R7, which means if we have a rod of length 7, then which statements will be true for that. Let us have a look at the statements. First one is saying R7 equal to 18, which simply means that the profit we can obtain by selling this rod of length 7 is 18. Let us check out if it is true or not. and this question is MSQ type, so multiple answers can be correct. Now looking at this price array, we can see that P of 7 has been given as 18, which means if we directly sell out that entire piece of rod of length 7 without cutting it, then the profit we can earn is 18. And that is what the first statement is saying, so that is true. Now coming to the next, R7 equal to 19. Now let us check out, is there any other way in which we can sell this rod and obtain a higher profit? We saw that if we sell it without cutting, if the whole rod is sold as itself, then we get a profit of 18. Now let us see if we can cut it out and then sell. Now what are the different combinations in which we can cut it? If we cut it into 2 pieces, then the possible options are, the 2 divisions would be 1 and 6, 2 and 5, 3 and 4. Now for each of these divisions, let us see what is the profit we can obtain. So for this first one, we'll sum up P of 1 and P of 6, which means 1 plus 17. So we get 18 from here. Then if we sell it in 2 pieces of length 2 and 5, then profit we'll get is this 5 plus 10, which is 15. Then if we sell it in 2 pieces of lengths 3 and 4, then the profit we get is 8 plus 9, which is 17. And among these, the highest one we got is 18. Now if we sell it in 3 pieces, it is possible for us to cut it in any number of pieces as long as the individual pieces are integer in length. So let us see, if we go for 3 pieces, then what are the possibilities? We can have 5, 1, 1, then we can have 4, 2, 1, then 3, 3, 1, 3, 2, 2, and along with this we can have, is there any other possibility? We can go for 2, 2, 2, that won't give us. So yeah, this is all the combinations we can have with 3 pieces. And again for each of them, let us calculate the profit. Now if length is 5, then we get 10, and if the length is 1, then we get 1 each. So that will be 10 plus 1 plus 1, which is 12. Then for 4, 2, 1, we get 9 plus 5 plus 1, which is 15. Then for 3, 3, 1, we get 8 plus 8, 16 plus 1, 17. Then for 3, 2, 2, we get 5 and 5, 10, and 8, 18. So again from here, the highest we have got is still 18. Now if we think about going for 4 pieces, then here the combinations we will be getting is 4, 1, 1, 1, then we can have 3, 2, 1, 1, then 2, 2, 2, 1, and there is no other possibility we can have. Now again for each of them, let us see the profit. 4, 1, 1 will give us 9 plus 3, 12. 3, 2, 1, 1 will give us 8 plus 5, 13 plus 2, 15. Then this 2, 2, 1 will give us 15 and 1, 16. So again, the highest till now which we have got is 18. Now if we think about going for 5 pieces, again it is not going to help. So instead of this, we can simply say that it is not possible to get a profit higher than 18. We can go for more 5 pieces, 6 pieces and 7 pieces, but we know that all it will involve is the maximum number of ones will be there, and P of 1 is just 1. So it is not possible for us to get a higher profit using those ways. So let us simply discard this second option. And now going for the third one, R7 can be achieved by 3 different solutions. Now it is saying that there are 3 different combinations in which we can obtain R7. So first combination which we saw is using 2 pieces. There we got 18 as our answer. Then with 3 pieces, again we got 18 as our answer. Now here with R7, what do they mean? The maximum amount earned by cutting a rod. So R7 is achieved does not mean that in how many ways can we cut the rod. There are multiple ways to cut. we can cut it in 2, 3, 4, 5, 6 and 7 pieces. What they are asking is, what are the different ways in which we can get the maximum profit by cutting that rod? And what is the maximum profit? It is 18. So in how many ways can we obtain 18? The first way is here by cutting it in 2 pieces. Second way is here by cutting it in 3 pieces. And the third way is without cutting it and selling it as a whole. Even that gives 18. As we saw here, P7 equal to 18. That is the third way. So yes, there are 3 different solutions for obtaining R7. And what is R7? The number of ways in which we can obtain a profit of 18 by selling this rod. So option 3 becomes true. Now coming to the last one, R7 cannot be achieved by a solution consisting of 3 pieces. We have just obtained it using the divisions 3, 2 and 2. So the statement becomes incorrect. So the answer for this question becomes 1 and 3. Both are correct. As per the question, they are defining an articulation point in a connected graph as a vertex such that removing that vertex and its incident edges will disconnect the graph into 2 or more connected components. So that is the standard definition of articulation point which they have elaborated. Now they're talking about let T be the DFS tree, or we call it as DFT. Now in this tree, we know that it is obtained by performing a DFS on that connected undirected graph G, and the resulting tree that we obtain after doing such a DFS traversal that we refer to as the DFT. So about that DFT, which of these properties hold true, that has been asked. So it is an MSQ question, multiple can be correct. So let us determine each of the option one by one and let's see which of that holds true. But before that, let us understand the definition of this articulation point once more. We know that if any vertex U is an articulation point in a graph G, then that vertex U will be a part of such 2 or more such components such that removing that will divide that graph into different components G1 and G2. Let us consider 2 components in this case. So here if we remove this vertex U from this graph and all the edges to which it was connected, then this graph will simply be divided into these 2 separate components and there will be no connection between them. No vertex of G1 will be connected to any vertex of G2. So now when can we say that this U is really an articulation point while performing a DFS? It will be true when we start the DFS from this node U and we go to any one of these 2 components at a time. Let us say we go to this component G1 first. Then while performing the DFS, we will visit all the vertices that are part of this particular component. Then while after this component is done, then we'll see that there is no more vertex left in this particular component, but the vertex U, which is still in the stack, is still having some unvisited nodes. So now they will become its child nodes and now those will be the part of this next component G2. So now from this vertex U, we will visit its unvisited children that will be lying in this component G2. So this is how this DFS will take place, and when this happens successfully, we will be able to say that this U was definitely an articulation point for this graph. Now let us consider these statements. Both the statements A and B are talking about the root of that DFS tree or the DFT. So the first one is saying that root of that DFT can never be an articulation point, and the second option is saying that root of that DFT can be an articulation point in G if and only if it has 2 or more children. So now let us take the same example and try to perform that DFS on this. Let us consider that this U is the root node. Now if this root has to be the articulation point in this graph G, then what will happen is it will definitely divide the graph in 2 or more components. Let us say 3 components now, G1, G2 and G3. So now when we perform the DFS, what will happen is starting from U, we will visit any one of its components at first. Let us say G1 first. We will cover up all the nodes lying in this particular component. Then when it will be over, then only we will move on to the second component, let us say G2. Then when that will be over, all the vertices in that component will be visited, then we will move on to the next component until all of them are done. So when this happens, when we'll be able to say that U is definitely an articulation point, considering that it is a root node, when it has these two or more components. If it had only a single component, then even after removing this U, all the nodes in this component would still be connected. In that case, U will not be an articulation point. So given that U is a root node and it has to be an articulation point, then there have to be two or more components, or in this case we can say the child nodes or the children of U. If we visit this G1 first, then we can say that it is the first child, and after that is done, then we go to G2, then that becomes its second child. So it is necessary for the root to have two or more children, or in this case the two or more components in which that will be dividing. Then only we can say that that root is an articulation point. So this proves that option A is wrong and B is correct. Similarly, let us go on to option C. It is talking about the leaf node of that DFT. It is saying that leaf of DFT can be an articulation point in G. Now coming to leaf nodes, we know that when we are actually visiting the leaf node of that DFT, then all the edges which are connected to that particular leaf, let's say this is the leaf node and there are multiple edges coming onto it, then when we want to visit this leaf node, then before that all the connected nodes to that particular leaf would already have been visited. So that leaf will be visited at the end. All its connected components, all its connected nodes will already be visited. So even if we remove this particular leaf from this DFT, it will not disconnect the graph. All of these components will still be connected because they are not taking the help of this leaf node for their connection. And hence, even after removing this leaf, the graph does not get disconnected, implies that this leaf is not an articulation point. So leaf node of a DFT cannot be an articulation point of that graph. So option C is also wrong. Then coming to the last one, if U is an articulation point in G such that X is its ancestor in T, T is our DFT, and Y is its descendant, then all the paths from X to Y must pass through that particular U, which is the articulation point. So for this, let's consider some examples. Let us say this U is the articulation point being considered. Then this is our ancestor X and descendant Y over here, and something like that is our DFT. So now in order to move from X to Y, there is only one path and that passes through U. So for such a kind of DFT, the statement holds true. But it is also possible that we have a DFT something like this is our U, X and Y, but there exists a path between X and Y, something like this, and on the bottom there are more nodes. So in this case, we will say that yes, here X is the ancestor and Y is the descendant, because first we are visiting X from U and then we are going to Y, then we can say that Y is the descendant of U. But here there is a direct connection between them and it is not necessary for us to go through U only. There exists another path between the ancestor and the descendant without involving this node U. So for such cases, the statement becomes false. It is not always necessary for us to pass through the articulation point. Hence, we'll say that the statement is also incorrect because it is not holding in all of the cases. So the only correct statement which we have got is option B. So that will be our answer. This is an operating systems question. We have been given 4 statements in respect to paging and we have to determine which of them is or are correct. So it is an MSQ type question. Statement 1 is saying that paging helps solve the issue of external fragmentation. Now, we understand the difference between internal fragmentation and the external fragmentation. The internal one occurs when, let us consider this is our memory. When does external fragmentation take place? When we have the space which is being wasted because of two different kind of structures. But when we divide this memory into equal sized chunks, let us call it, that is called as a frame. And on the other side, if we have this as a process, then that process is divided into the same size chunks, and that is called as pages. The frame size is equal to the page size, and every page goes and sits into one of the frames. So when this occurs, the external fragmentation gets reduced. That is because every single page is occupying one single frame. So there is no wastage of space in between. But only, let us consider, this is our page, but it is not completely occupied. It is only having, let's say it is only half filled while half of it is left empty. So only this much space will be wasted, the half of the page. Let us say the process requires 4 pages, but out of those 4 pages, the last page is only half filled. So in reality, that process is requiring just 3.5 pages, but we will give it 4 pages. So only the bottom half, last page is wasted. That is called as internal fragmentation. And in this case, as we saw, there is no external fragmentation. So yes, paging does help to solve this issue, because the wastage will only be between these pages, or you can say between the in a single frame, not between those frames. So yes, statement 1 is true. Next one is saying that page size has no impact on internal fragmentation. Page size does have an impact. It tries to reduce the fragmentation, but just to an extent. Internal fragmentation still persists when we are using the concept of paging. So this statement can be said to be false. Third one is paging incurs memory overheads. Now, when we divide a process into pages, then we have to maintain something, a structure called as page tables, which records which page is put into which frame. It has a page number and its corresponding frame number to indicate the mapping between these pages and the frames. So this structure has to be stored again in the memory. It is again stored into pages, so that requires some memory overhead. So the statement C is true. Last one is saying multi-level paging is necessary to support pages of different sizes. Now, all the pages and all the frames are of the same size basically. But when do we incur this multi-level paging concept? It only occurs when, let us say, our process size is so large that it is divided into multiple pages, and all these pages data, their corresponding mapping would be filled into this page table. But it might so happen that this page table grew so large that it cannot be occupied in one single page. Then in those scenarios, we need to use multiple pages in order to store that particular page table itself. So that is when multi-level paging comes into the picture, and not when we have pages of different sizes. That is not correct. So this option D is false. We'll be going with just A and C. This is an operating systems question based on CPU scheduling. We have 3 processes which arrive all at the same time, 0 units, with their CPU burst times of 16, 20 and 10 milliseconds respectively. The scheduler has prior knowledge about the length of the CPU burst, which means it already knows their burst times as 16, 20 and 10. So in this case, the minimum achievable average waiting time for these 3 processes in a non-preemptive scheduler will be how much? So in this scenario, they have not given us which scheduling algorithm has to be used. We have to decide that ourselves based upon these 2 facts, that the algorithm has to be non-preemptive and CPU has the prior knowledge of their burst times. So in that scenario, what are the possible algorithms we can look for? FCFS can be used, but all of them are having the same burst times. They will be executed in the same order. It is a valid candidate. We can check for that. Then next comes shortest job first. That is also possible. It is non-preemptive, and with the given burst times, they can be executed in the order of 10, 16 and then 20. So this is also a valid candidate to be checked. Apart from that, if we go for round robin, it will become preemptive. SRTF again preemptive. So they will not be possible for the scenario. We'll just check for FCFS and SGF, that which of them gives the minimum achievable waiting times. So let us trace out their Gantt charts and check out. For FCFS, there is another problem here, that they have not clearly mentioned that this process has arrived first followed by these two. They have just said that all of them arrived at the same time. So if we go to assume that they might have arrived in this given order 16, 20 and 10, then we can check for that. Otherwise, they have not clearly mentioned what was their order of arrival. Still, let's see what do we get. Let us call the processes as A, B and C. So first, this would be the table. Arrival time is 0 for all. Burst time, completion time, turnaround time and the waiting time. Okay, so the burst times is 16, 20 and 10 for the processes A, B, C. They will be completed in the same order. This is timeline 0 up to 16 it will execute. Then from 16 to 16 plus 20 means 36. B will execute. Then C will execute up to 46. So their completion times would be 16, 36 and 46. Turnaround time will be given as completion time minus arrival time. Arrival time is 0 for all. So turnaround time will be 16, 36 and 46 respectively. Now this burst time is given as turnaround time minus of waiting time. Sorry, the turnaround time minus of burst time. That gives us waiting time. So that will be 16 minus 16, 0. 36 minus 20, 16. Which means the process B arrived at time t equal to 0 and it executed from 20 for 20 seconds from 16 till 36, which means it waited for this particular duration of 16. Similarly, process C that waited from 0 till 36. 46 minus 10, 36. So this is the time it waited for. So the sum of their burst times is 36 plus 16, which is 52. And if we take out the average, 52 by 3, it would be something about 17. So now let us check for the shortest job first if it gives the better performance. So for that, we'll again do the same thing, trace out the Gantt chart and see what is the waiting time we get for that. And we'll also note down the average waiting time which we got for FCFS, which was about 17. Now for the shortest job first, this is the burst time for the processes A, B, C, 16, 20 and 10, completion time, turnaround time and waiting time. So the first process to be executed now will be C because it is having the smallest burst time. So it will execute from 0 till 10. Next will be A from 10 till 10 plus 16 means 26. Then finally B from 26 to 46. Their completion times will be A completed at 26, B at 46 and C at 10. Their turnaround times will also be same because their arrival time is 0. Now waiting time will be turnaround time minus burst time. So for A it is 10, for B it is 46 minus 20 means 26 and here it is 0. So the sum is 36, that divided by 3 gives us 12. So this is definitely lesser than for FCFS. Hence the SJF scheduling algorithm will give us the minimum achievable average waiting time for these 3 processes and that time is 12 milliseconds. So the answer for this question would be 12. A second question based upon instruction sets. They have given the following instruction sequence where R1, R2 and R3 are the general purpose registers under consideration and memory of X is the operation that denotes the content at the memory location X. Now this is in the tabular format we have been given the instruction sequence which will be executed and at the end of that we need to determine what will be the output. And the details are given over here, assuming that the contents of the memory location 5000 is 100. So initially at the location 5000, the content stored is 10 and the content of the register R3 is 3000. So R3 register is initially containing 3000. The content of each of the memory locations from 3000 to 3020 is 50. So now from the memory locations, you can denote like this: from 3000 till 3020, all of them are having the same data, that is 50. Now the instruction sequence given in the tabular format starts executing from the memory location 1000. So this is where the instruction set starts execution. All the numbers are in the decimal format. Assume that the memory is byte addressable. So after this execution of the given program is complete, we have to determine what will be the content of the memory location 3010. Initially it will be lying over here, so its initial content is 50. After the execution of this instruction set, we have to determine what will be the updated value in that location. So now coming to the instruction set, we have been given the instruction and its semantic as well for us to understand what is it exactly doing. And this is the size of the instruction, how many bytes is it consuming. That is not really of any use to us. Let us have a look at the instructions, what they are doing. The first one, MOV R1 5000. So what this instruction is doing, it is moving the contents of memory location 5000 into the register R1. So what do we have at location 5000? We have 10. So in R1 we will be moving the data content as 10. Then MOV R2 R3, which means we are moving the content of the location given by R3 into register R2. Now in register R3 the content is 3000. So we are not moving 3000, we are moving the content at memory location of R3 into R2, which means the location 3000, the content at this location will be moved to register R2. So R3 has data 3000 and content at that data given by this, what is it, 50. So this 50 is actually being moved to R2. Next, add R2 R1, means we are adding the contents of both and then writing the result to the R2 itself. So after this, the R2 will get the content as 10 plus 50 equal to 60. Next, MOV R3 and R2. Now here we can see R3 is used with the parenthesis, which means not R3 register itself, but the memory location given by the address stored in R3. What's the address in R3? It is 3000. So at the memory location of 3000, we are storing or we are overwriting it with the contents of R2. So now at 3000, what do we initially have? 50, but now we are overwriting it with the contents of R2. So this becomes 60. Next, increment R3. Now R3 is having 3000, so it will be incremented to 3001. Next, decrement R1. What is R1 having? It is having 10. That is being decremented by 1. So now this R1 gets 9. Now next instruction is BNZ 1004. What is BNZ? Branch if not 0, which means this is a loop actually. Until and unless we get the value 0, we have to keep looping. And how are we looping? We are going back to the memory location 1004. Now we know that the execution started at location 1000. And this loop condition is just after the decrement R1. So unless the value stored in this R1 becomes 0, we will keep looping. We will go back to the start and we will execute the same sequence of instructions once again. So right now the value in R1 is 9 and it keeps on decrementing by 1 in every iteration of the loop. So 9, 8, 7 and so on, it will continue. So just trace out the loop. It will execute a total of 9 times. from the value of R1 9 till 1. And in every iteration of the loop, what is the main thing we are doing? In every iteration, these are the two important instructions we are executing. We are incrementing the value of R3 by 1 and we are decrementing the value of R1 by 1. Other than these two instructions, this rest of the part is not actually doing any important functionality, and this reinitialization will not take place in every iteration of the loop. We will simply be working with these two instructions. So let us trace out those 9 iterations of the loop. The values of R3 and R1 we are writing. Initially it is 3001 and 9. In the next iteration they will be changed to 3002 and 8, so on till 3001, 3000. This R3 is incrementing and this one is decrementing. So at the end what happens is this changes to 3001, 2 up to 3009, let us say. Let us write it properly. So when R3 will be 3009, then R1 would have turned to 1. Then in the next iteration this will be 3010 and 0, but here this will not actually be iterating over because the instruction is branch not 0. So when R1 becomes 0, the iteration will stop over here and this will not loop further. So we are executing until this point itself. Now this is our loop, and after we come out of the loop we are halting. So this is the 9 number of times, 9 iterations we have traced out, and in every iteration what we are basically doing, we are changing the values given by the corresponding. We can have a look over here. In this particular instruction we are moving in R3 the contents of R3, the value of R2. Like in the current instruction which we were watching, the contents of R2 were 60 and we wrote that at the location 3000. So in the next iteration 3001, that would be changed with something, then 3002, that would be changed with something, but we are moving only till 3009. So by the end of the loop we will be performing M of 3000 of 9. In this location we would be storing the contents of R2 at that time, not the current contents which is 60. At that time whatever will be the contents, that would be stored at the location 3009, and that would be our last instruction, after which we will be halting. So basically looking, we are not changing the value at the location 3010 because we stopped before that itself. So the initial value which was there in that location, that will stay the same, it is not being altered. So initially there was 50 in this location and we are not changing it even after execution of the given instruction set. So that will be same as 50 at the end of the instruction as well. Hence after execution of the program, the content of memory location 3010 is still 50. So that will be our answer. Next question from the data link layer. They have given a sliding window flow control mechanism that is operating between a sender and a receiver over a full duplex error-free link. And for this link we have been given the following characteristics. We have to assume that the time taken for processing the data frame by the receiver is negligible. So the propagation delay which we have, that is taken as negligible. The time taken for processing the acknowledgement frame by the sender is negligible, which means for processing the acknowledgement sent by the receiver, the sender will not need any propagation delay, and that acknowledgement delay has also to be assumed as 0. And the sender has an infinite number of frames available for transmission, that has to be assumed. Along with that, now the exact data has been given. The size of data frame, which we call as L, is 2000 bits. the size of the acknowledgement frame is 10 bits. So here we are dealing with both the data frame as well as the acknowledgement frame. So this was LD for the data frame and LA for the acknowledgement frame. The size given is 10 bits. And we have to assume the link data rate, which is nothing but the bandwidth in each direction, is 1 Mbps. So bandwidth is given as 1 megabps. Here all of them are dealing with bits and not bytes. Finally, the one-way propagation delay of the link is given as 100 milliseconds. So that is nothing but the TP, which we refer to as the propagation delay, that is given as 100 milliseconds. So now, using all this data, what we want to calculate is the minimum value of the sender window size in terms of the number of frames to achieve a link utilization. What is link utilization? The efficiency. The efficiency to be achieved is 50%. So what is the number of frames? Now this is a sliding window protocol. So the size of window will not be 1, it will be greater than that. So we'll assume that to be n, and we have to calculate the value of n given all these parameters. So now let us assume, what is the formula which is used for calculating the efficiency? It is given as useful time upon total time. So in this case, what will be the useful time? There are n frames, and for each frame the time required for transmitting that frame, which we call the transmission delay, TT, but this TT will only be calculated for the frame and not for the acknowledgement, because sending an acknowledgement is not useful. That is the wasted time itself, that is the useless time. So that will be calculated here in the useless time thing. So at the bottom we will have TT for the frame, then we will have TT, the transmission delay, for the acknowledgement, and along with that we have twice the propagation delay. They have only given the one-way propagation delay, but between the sender and the receiver, the propagation delay has to be considered 2 times. This one for the data frame and this one for the acknowledgement, so that TP gets considered twice. So this is the formula we'll be using. Let us substitute all the values given. Now efficiency to be achieved is 50%, so that will be 0.5 equal to n, which we have to calculate. This side, let us find out the TT and the TP for everything. The TP, propagation delay, it is already given as 100 milliseconds. So that is there. We have TT for the frame. How is TT given as? The size of data to be sent upon the bandwidth, or L by B. The data frame size we already know is 2000 bytes. The bandwidth given is 1 Mbps. So we'll write that as 10 power 6 bits per second. There's no need to convert bits into bytes. So this we get in seconds, and we can cancel out 3 of these. So this will become 3, and that becomes 2 milliseconds. Similarly, we calculate the transmission delay for the acknowledgement packet as well. For that, the size given is simply 10 bytes, and the bandwidth will be same for that, which is again 10 to the power 6 bits per second. So this we get in seconds, so that we will be converting back into the milliseconds. So this will become, originally it is 10 by 10 to the power 6. We can cancel out this 1, it will become 5, and then we will remove 3 of it to convert it into milliseconds. So that will be 1 by 10 square milliseconds. So that becomes 0.01 milliseconds. So now we have got all of that, and we will simply substitute them over here. So let us see what do we get. The TT for the frame we have got as 2 milliseconds divided by the TT for the frame, which is 2 milliseconds, plus the transmission delay for the acknowledgement packet, that we got as 0.01 milliseconds, plus 2 times the propagation delay, which is 100 milliseconds. So this becomes 100. So now from this we have to calculate the value of n. So let us do that here, erasing this out. Now we will write this entire equation with respect to n. So we'll have n on one side and we'll shift everything else on the other side. So we will get n equal to 0.5 times of 2 plus 0.01 plus 2 into 100 is 200, and this whole thing will be divided by 2. So let us see what do we get. This is 0.5, that we can write as 5 by 10. So 5 by 10 with this 2, that becomes 20, and here we have 202.01. So let us calculate. What do we get? This we can simply cancel out 4 times. So we get 202.01 by 4, which becomes 4 5s 20, then 50. So we get 50 point something, 50.50, but we have to take rounded off to the nearest integer. So we will be taking the seal of this, because if we are requiring half a window, then we will take whole of that window instead of removing that out. So ceiling will be required instead of the floor. So 50 point something is there, and when we take seal of that, then that would become 51. So that will be our answer. When the window size is 51, then we can achieve 50% efficiency given all the following constraints. So answer for this question has to be 51. This is a TOC question based upon Turing machines. We are having a Turing machine M and its encoding has been given, based upon which these two languages have been formed, L1 and L2, and we have to comment about their decidability. So let us first understand what these languages are. L1 is giving us an encoding of Turing machines M that take more than 2021 steps on all the inputs, while in L2 they are talking about taking those many steps by the Turing machine but only on some inputs. So that's the only difference. Here we have all, and here we are having just some inputs. So how can we comment upon this? So let us first understand that what we'll be doing over here is we will try to execute this Turing machine M for at least 2021 steps, 2021 plus 1, so that in this step we will check if it is halting or not. So we will try to execute them on all the inputs of length less than or equal to 2022, and this will be a finite set. Why so? Because if k is the set of alphabets for this Turing machine, then there would be k to the power 2021 possible inputs having length that we require. So that this will be a finite set on which we will be running this Turing machine M for those many steps. Then what will happen as an outcome? We will see that M will take more than those many steps on all the inputs. Now by all here we mean all having length less than that, even more than that. Here by all we mean less than 2021 as well as greater than 2021. So that is all. If it takes more than those many steps on all inputs of length less than. So here we are having a restricted domain. We are saying that if it is taking 2021 and greater steps on this set 1, then it will definitely take those many steps on all the inputs, means set 1 plus set 2 combined. So this is a restricted set. If this is satisfying, then only we will comment about the entire S1 plus S2. These are the two sets of inputs. So if S1, if in S1 all the strings pass, then we will say that yes, it is true that it will take more than those many steps on all the inputs. Otherwise, no, which means we are able to comment either yes or no, if it will happen or it will not happen. And this is what we mean by decidability. Hence, this language L1 is definitely decidable. So L1 is decidable. And in the same way, when we check out for this L2, the only difference is that instead of all strings, we are talking about some strings. If in this set S1, only some strings are satisfying this criteria that they are taking more than 2021 steps, then we will be able to say that in the combined set in this entire language also, only some strings may be able to take those many steps, which means M will take more than 21 steps on some input, which means if even S1 is not getting entirely satisfied, then how will the S1 plus S2 both will be? If S1 clears, then S1 plus S2 may clear or it may not clear. But if S1 itself is not getting cleared, then S1 plus S2 will never get cleared. So that is what it is. We are in this case also able to comment after checking for S1 whether it will satisfy on both or not. And why we are checking only on S1? Because S1 is finite, but this S2 is infinite set. We cannot check on this entire set S2. So we are only checking on the S1, and then based upon its result, we are commenting whether it will be possible for both or not. So again, in this case, we are able to comment yes or no on this. So this becomes decidable again. So L2 is also a decidable language. Hence, we will be going with the option first, that both L1 and L2 are decidable. So that is correct. This is a compiler design question. There are two statements and we have to determine which of them is or are true. Now this S1 is saying that the sequence of procedure calls corresponds to a pre-order traversal of the activation tree. Now what exactly do we mean by this? We know that whenever the procedure calls are made, which means it is like a recursion call. For making a recursive call, what do? We use a stack and we create the activation records which are pushed into the stack. And at the same time, it is saying that the sequence in which the calls are made, which means if we have any recursive function, let us say f of n equal to f of n by 2 plus k, something like that, then what will happen? If we try to trace it out in the tree format, then it will look something like this. We have f of n here, then it will branch out into f of n by 2 and f of n by 2. Then they will further branch out until we reach the base condition. Until that is hit, we will keep calling the procedure calls. So that is what it is talking about, that the sequence in which the calls are made, that corresponds to pre-order traversal of this activation tree. That is what it is trying to say. And then in the same way, we have the statement S2, which is talking about the procedure returns. So in the same way, in S1 we were talking about the calls, and in S2 we are talking about the returns, which means the order in which we return from those function calls, that corresponds to post order traversal of the activation tree. So that is what we mean by both these statements. Now let us verify which of them is or are true. So for example, we have considered this particular activation tree over here. We are not actually concerned what exactly does it correspond to or which recursive function does it belong to. We simply have an activation tree and we will identify the sequence in which the procedures are called and returned. So for that, there are these two statements that we need to consider, that a parent function calls its child function. So as we had seen here, f of n will call its children, that is f of n by 2 and f of n by 2. So always a parent is called before its child. A parent itself calls its children. So this is what we use while calling. And similarly, while returning, what do? The child function is returned before its parent, which means while returning from the function calls, first both of its children or one of its children will be returned, and after that the parent will be returned. As you will see, both the children are returned, and then when they return their values to their parent, then the parent returns the final value. So that is how the recursive calls are made. So now if we have this particular tree, here A is the parent. So we will proceed like this. A will call its first child, that is B. So now B becomes the parent. It has two children, so it will call its first child, that is D. So on the other side, let us also note down what is the calling order that we are getting. So first we start with the root, that is A. After that we went to its first child, that was B, then D. After this D is done, it will return. So this is the point where we are returning. So that is D is the first activation record from where we are returning. After that, we go back to B, nothing happens there. Then we come to E. The first time we hit E, it signifies a procedure call. So E is called. Then we come here, it has no children, so it will return. So here E is returning. So it is the second child node to be returned. From that we come back to B, and B has no more children, so again that will return. Now coming to A and moving to its next right child, that is C. So C is called next. Then C has no children, so it will simply return. Then from C we come back to A and return the final value. So we have traced out what are the orders in which the procedures are called and what are the order in which the procedures are returned. And if you look carefully, this A, B, D, E, C, this is nothing but the pre-order traversal for this tree. And in the same way, the order in which they are returned, that corresponds to the post-order traversal of the given tree. And that is what both of these statements were saying. So we see that both the S1 and S2 are true. So we'll be going with the third option, that is both are correct. This is a group theory question. We have been given a group G that has the order 6. And we also have H, which is a subgroup of G that has order between 1 and 6. The boundaries are excluded in this case. So based upon this information, we need to comment about the cyclicity of both G and H. So how can we do that? For this, we have the Lagrange's theorem, which says that the order of a subgroup always divides the order of a group. So if H is the subgroup of G, then we know that the order of G is 6. So what are the possible orders for H? 1, 2, 3, 4, 5 and 6. But they have already said that it lies between 1 and 6. So the boundaries are excluded. Also, the order of subgroup must divide the order of group, which means the order of H must be divisible by 6. So 4 and 5 are also excluded. Only 2 and 3 are the possible orders for the group H. So now, how can we comment on their cyclicity? Using the second theorem, that every group having a prime order is cyclic. But vice versa of this statement is not true, that if the order is non-prime, then we cannot say that it is not cyclic. In case of non-prime, it may or may not be cyclic. Both are possible. So as we can see over here, the order of group G is 6, which is non-prime. So G may or may not be cyclic. We cannot say for sure. But in case of H, both of its possible orders 2 and 3, both of them are prime, which means H will definitely be cyclic. For G, it may or may not be cyclic. We cannot directly say just by looking at its order because it is non-prime. So the correct output will be G may not be cyclic, but H will definitely be cyclic since it has a prime order. For G, we cannot comment. So the correct choice to go would be the second option. This is a mathematics question based upon sets and relations. They have defined a relation R to be circular if A related to B and B related to C together imply C related to A. So we already know three types of relations, that is reflexive, then we have symmetric, and we have transitive. And in addition to this, they have defined a new type of relation, that is circular. Let us understand what are all these. In reflexive, what do we have? A relates to A. Similarly, B relates to B and so on. But in symmetric, what do we have? If A relates to B, then that implies B relates to A. Means vice versa. In transitive, what do we have? A relates to B and B relates to C, then they together imply that A also relates to C. And in the circular, which is a new type of relation that they have defined, they are saying that if A relates to B, B relates to C, then they together imply that C relates to A. So this is the only difference between transitive and circular. So now we have these four types of relations, and based upon this, from the given options, we need to determine that in which of these cases will S be an equivalence relation. When do we say that a relation is equivalence? When it is reflexive, symmetric, as well as transitive. All the three are satisfied. So let us check out. In the first option, it is saying that S is reflexive and it is symmetric. Then will it be equivalence? It is just reflexive, which means A relates to A, B relates to B, C relates to C. And it is symmetric, which means AB will imply BA and so on. But using these two, we cannot establish whether it will be transitive or not. It is not possible that such a relation will be transitive, because these reflexive and symmetric put together, they cannot derive transitive, because if that were true, then there was no need of transitive. Only if a relation was reflexive and symmetric, we would have said that it is equivalent. But that's not true. Hence, the first one will be not an equivalence relation. Then second one is saying that it is circular and symmetric. Now let us see if using these two, we can derive all the three. In this one, the relation is said to be circular and symmetric. So by symmetric, what do we mean? A relates to B implies B relates to A. And in circular, what do we mean? A relates to B, B relates to C. Put together, they imply C relates to A. So let us check that whether from these we can establish the reflexive and transitive properties or not. Now, as we can see, the relation is symmetric. So if this is able to determine C relates to A, then it would also be able to determine A relates to C, and that is what becomes our transitive property. So in this case, symmetric and transitive are both being satisfied, but the reflexive will not be satisfied. That will fail. Hence, we do not have all the three being satisfied, making it not an equivalence relation. Then in the same way, let us check out if in the option 3 we are able to derive all the three properties, all the three relations holding true or not. So in the third one, we are having the relation as reflexive and circular. It is reflexive, which means A will imply A relates to A and B relates to B. It is circular, implies that A relates to B, B relates to C. Put together, they imply C relates to A. Now here we can say that since it is reflexive, let us say A relates to A and A relates to B are put together. Then after applying the circular property on this, what this will derive? The last one derives the first one, which means it will derive B relates to A, which means we are able to derive the symmetric property. Combining these two, we are able to derive the third property, that is symmetric. Let us also check out if we can derive the transitive property or not. For that, what we can do, we know that it is reflexive and it is symmetric as well. So if we apply this in the circular property, it is able to derive C relates to A, and after combining it with this symmetric property, we will be able to say that it is also able to derive A relates to C. So A with B, B with C, they will be able to imply A relates to C. So that is our transitive property, which means we have derived all of them. Reflexive was already given and we derived symmetric plus transitive. So all the three are covered, and hence this implies that the relation is in this case becomes a equivalence relation. Let us also check out for the last one and see if it can also hold true. In the last one, it is given that it is both circular as well as transitive. So using that, what happens? It is transitive plus circular, which means A relates to B, B relates to C. Here implies, in case of transitive, it implies A relates to C, and the same thing in circular will imply C relates to A. So just using these two, we have to check if both symmetric as well as reflexive can be established. But as it can be seen over here, using these two, A relates to C and C relates to A means the vice versa of each other can be derived, and that can take us to the symmetric property only, but reflexive will not be holding true. It cannot be established using these three. So since all of them are not being satisfied, even the last one fails to be a equivalence relation. So the only third option is correct. In this case, S is an equivalence relation. So we will go with option 3. This question is based on Boolean algebra. We have been given a Boolean expression f, and from the given options we need to determine which of them is or are equivalent to f complement. So first of all, let us find out what is f complement, and then we shall check all the options one by one. So f is given to us as x plus y plus z, or you can say or, then ANDed with x bar plus y, y bar plus z. This is our f. So f complement will be this whole thing complemented. So we can simplify this using De Morgan's law, that this complement will be distributed on all the three terms and the AND will convert into OR. So these two are ANDed with each other, these two are ANDed with each other, so that will convert into an OR operation. So what we get as a result is x plus y plus z, the whole complement, ORed with x bar plus y complement, and that ORed with y bar plus z complement. Again we shall apply De Morgan's law on all the three. That will give x bar, y bar, z bar plus x bar and one more bar, because this complement will be distributed over them, so that will just cancel out and we will be left with x y bar plus of y complement and one more complement, so that will also cancel out, giving us yz bar. So this is what we have got f bar as. Let us see if we can further simplify that. What you can do is we can take y bar common from these two. So that will give y bar x plus x bar z bar plus yz bar. Now what we can do is, here we have x and x bar, so we can apply distributive law, or can be distributed over AND. So this will give us x plus x bar and x plus z bar. Now this x and x bar will give us 1, so there is no need to write that. So we can simply go for y bar, which we already have outside, that with x plus z bar, and the last term we have is yz bar. Now we can write this as x y bar plus y bar z bar plus yz bar. Now from the last two terms we can again take z bar as common. That will give x y bar plus z bar. What will be left is y plus y bar, which is also 1. So this is the final value of f bar which we have got. Let us note that down here, x y bar plus of z bar. Now we can check all the 4 options one by one. Let us start with option A. It is given as x bar plus y bar plus z bar ANDed with x plus y bar ANDed with y plus z bar. Now we don't have to take its complement. We'll directly check if it is equivalent to this f bar or not. So what we can do is we'll simplify the expression. We can multiply the brackets with each other and let us see what the result is. So we can start with these first two brackets. That will give x bar ANDed with x. So it is 0, no need to write that. We'll have x bar y bar plus y bar x plus y bar and y bar. So we can write that only once, plus z bar x plus z bar y bar. And the last bracket is added as it is left out, y plus z bar. So this gives us the first 3 terms all are having y bar. Even the last term is having y bar. So we can combine all of them into a single y bar. So we have y bar plus z bar x multiplied with y plus z bar. Now we multiply both the brackets. Y bar and y will cancel out. So we get y bar z bar plus of xy z bar plus of z bar x. Now again what we can see is there is z bar common in all of them. So we can take that out. Let us write that here. Yeah, we are taking z bar as common, then we'll be left with y bar plus xy plus x. Now as we can see, these two terms, they are having y and y bar. So again distributive law can be applied. It will give y bar plus x and y bar plus y, which is 1. So there is no need to write that. And there is one more x that will also get added to it, resulting into the same thing. So what we get is y bar z bar plus x z bar. That is not matching with the f bar value which we have got. So option A is incorrect. Let us check for the other options as well. Let us erase this out in this thing. And now let us check for the option B if it can give us the same result as f bar or not. And this is a MSQ type question, so there can be multiple options which are correct. Alright, so option B is given to us as x y bar plus z bar, and as we can see it is already in the simplest form, same as the value which we have got for the f bar, x y bar plus z bar. So there is actually no need to check this. This option is directly correct. Let us now go for the option C. It is x plus z bar y bar plus z bar. So let us expand it out. X y bar plus x z bar plus y bar z bar plus z bar. The last three terms are all having z bar as common, so we can simply write one single z bar, and this is again of the same form as f bar. So this option C is also correct. Now then let us check for option D. That is given to us as x y bar plus y z bar plus x bar y bar z bar. And as you can see, this x y bar, that is the same term we have here. Y z bar we are having over here, and then x bar y bar z bar is also there. And what is this on the left hand side? This is the step where we were calculating f complement. So all of these values are actually f's complement, and finally we had resulted into this step. So what is given in option D is an intermediate step which we had further simplified while calculating the value of f complement. So definitely this value also represents f complement, but not in the very simple form. And hence from this we can say that option D also resembles, it is also equivalent to rather f complement. So B, C and D are all correct answers. That will be our answer. This is a computer networks question. We are having two hosts P and Q that are connected through a router R. So this is how we can draw this particular configuration. Two hosts connected in between using a router. And then they're saying that the maximum transfer unit, that is the MTU, or the size of the maximum segment, the maximum size of the segment that you can transfer through that link is said to be its MTU. So the MTU of the link between P and R is 1500, means for this particular link, MTU is 1500 bytes, and for this link between R and Q, it is 820 bytes. So what we want to do is a TCP segment of size 1400 bytes. This particular segment has to be transferred from host P to host Q. So there is no other path from P to Q. We will have to go through this intermediate router and then transfer that packet to the host Q. So it has to go through R, and it is saying that the identification number or ID value of this particular packet is 1234. So as we know, this identification field is there in the TCP header, which helps the receiver to identify that all the frames having the same ID bits belong to the same segment. Because when we have a segment and that is fragmented into multiple pieces, then all of them get the same ID bits, and this ID along with the flags that we have, the MF, DF, those flags together with ID helps us determine that all of these fragments belong to the same segment and the order in which they are to be reassembled. So for this one, ID is 1234. We have to assume that the IP header is 20 bytes in size, means there is no extra overhead, it is simply 20 bytes. Option field is not used. Further, the packet is allowed to be fragmented, which means the fragmentation is enabled. The DF flag is not set by the sender. So for the situation, which of the following statements is or are correct? So before going through that, let us understand how this particular transmission would work out. Because as we know, from P to Q there are two different links. Let us call this as link A and this as link B. So we have to pass this particular segment through two different links. And as we can see, both of them are having different MTUs. So in order to send it from P to Q directly, we are having two different ways. Either first find out the bottleneck bandwidth, which is 820 bytes in this case, and directly send the segments of that particular size. But the thing is, how will we know what is the bottleneck bandwidth? There is a procedure using ICMP. We use this particular method for MTU discovery of a path, but there is no mention of using that thing over here. So we will not consider this situation. Another one can be, we will first send this packet directly to the router R, and then this router will decide, because anyways fragmentation take place at the router itself. So this router will then decide that in which way should we fragment the packet in order to send it through this particular link, which means according to this second MTU, this router R will perform the fragmentation. So what we'll actually be doing is, the way in which this particular fragmentation will work out is that P will send the packet of 1400, and anyway it is allowed in this particular link because its MTU is 1500 bytes. So this packet of 1400 bytes along with a 20 bytes header, that will be sent through this particular link A, and it will be received at this router R. But now this R will sense that the MTU of this next link is just 820. So now it will have to perform the fragmentation. What it will do, this is the data, this is the header which will not be used. It will later be appended to all the fragments that are created. So for this 1400 bytes data, what it will do is it will create two fragments, and as we know the rules of performing fragmentation, the size of the data should be a multiple of 8 except for the last fragment. So what it will do is it will create two fragments. First will be of 800 bytes, because that is the maximum that is allowed, because 800 plus 20 bytes header will exhaust this MTU. So it will create the fragments of 800 bytes and 600 bytes. Then this 20 bytes header would be appended to them, and then these two fragments would be sent through this link B. So now both of these fragments, let us see what will their flags be. This is the first fragment and this 600 is the second fragment. So for this one, let us see what these flags will be. For the first one, MF flag will be 1 because more fragments are following it, but for the second one it will be 0. Similarly, the DF flag, it will be 0 for, it can be 1 for both, because more fragmentation is allowed or not allowed, that actually depends. But in this particular link, there is no need for further fragmentation. So we are not even concerned with this don't fragment part. We can say that it is 0. It may be allowed if there are more routers or even shorter bottleneck bandwidth somewhere ahead in the path. So let us say it was sent as 0. So this is how it will be sent through this particular link. And now let us see what are the options. First one is saying that two fragments are created at R and the IP datagram size carrying the second fragment is 620 bytes. So now as we saw, these segments, this is our segment. In that we have this data part and the header part, and this segment is then put inside the IP datagram and then that is transmitted. And we also know that there is frames as well in the data link layer in which this entire IP datagram is put. So that is how the transmission works out. Here talking about this particular layer, in the network layer, the IP datagram size carrying the second fragment, means this one, will be 620 bytes. So yes, it is true, because here the datagram size, what will this datagram size mean? It will consist of the segment size plus its header, which in this case is 620 for the second one. So option A is true. Coming to the second one, if the second fragment is lost, then R will resend the fragment with the IP identification value as 1234. So now one thing to be considered here is the original segment had the ID bits as 1234. So both of its fragment will also get the same ID bits. But the thing is, if the second fragment is lost, then this receiver Q will come to know that, because it will receive the first fragment and it will see the MF flag as 1 in it. So it comes to know that there must be more fragments following it, but it has not received any. So Q understands that some fragment is lost. So it will intimate somehow using ICMP packets, so there are some strategies for that. So it will be intimated to the sender P, but now P does not know that exactly which fragment is lost. So instead of sending only the lost fragment, because anyway fragmentation is performed by router and not the host itself. So instead of sending the fragment, what P will do, the sender P will transmit the entire segment once again. So the next time R will again have to fragment it and then send it out. Then at that time Q can discard the first fragment because it is received multiple times and take the second one. So that is how this may work out. But here the thing is, the same fragment will not be sent out, but the entire segment would be sent. So that makes B incorrect. Next, coming to C, if the second fragment is lost, P is required to resend the whole TCP segment. That is what we just saw, it is true. The last one is TCP destination port can be determined by analyzing only the second fragment. Now, as we know, in the TCP header, there is a field for source port number and destination port number. And this particular header is present in all the fragments, not just the second fragment. So if we want to determine this destination port number, then we can use any of the fragments that we have received and not just the second one or just the last one. So there is no restriction on that. Any fragment can be used for this purpose. So that makes option D also incorrect. So we will be going with A and C as the correct answer. An engineering mathematics question based upon matrices. We are having this 4x4 matrix, let us call it A, and they are asking us to find the largest eigenvalue for this matrix. Now, how do we find the eigenvalues? The traditional way we go for is, we find its characteristic equation first. Let us say this is our matrix A, so we will find out A minus lambda I equal to 0, that will be its characteristics equation, and then we will be finding its roots. The value of the largest root of this equation will give us the eigenvalue for this matrix. So let us see how can we do it. We want to get this determinant of A minus lambda I, and that will give us the characteristic equation. So this I is the identity matrix of order 4x4, and when we do A minus of lambda I, then what will that become? This is our matrix A, and from this we'll be subtracting a 4x4 identity matrix multiplied by lambda. So what will that matrix look like? As we know, identity matrix is having 1 only in the main diagonal, and remaining all of its elements are simply zeros. So when this identity matrix it's multiplied with lambda, it will become like this. Only these 4 elements will be lambda and all of the remaining ones will be 0. So let us write down A minus lambda. So that will give us a matrix. Let us say like this. All these ones will remain 1 because from them the 0 is getting subtracted. But from these zeros in the prime diagonal, we are subtracting the lambda. So that will give minus lambda. So it will be like this. 1 minus lambda 1 1 1 1 minus lambda 1 and here again triple 1 and minus lambda. So this is our A minus lambda I. So for this we need to find out the determinant and then get the characteristic equation. But as you can see, it might be difficult to get the determinant for this 4x4 matrix. So let us try to apply some transformations on it. Some row and column transformations. Let us say we are doing R2 equal to R2 minus R1, but before that it will be better if we try to get rid of this lambda. So let us do it this way. Let's say R1 equal to R1 plus R2 plus R3 plus R4. That will help us get all of these terms together and then we can take out something as common. Let us see. That will give us, we are adding all the 4, so that will give 3 minus lambda in every row. So that becomes 3 minus lambda, 3 minus lambda everywhere, and the remaining rows will be same. Minus lambda 1 1 1 minus lambda, it is 1 and 1 1 minus lambda. So now we can take out this 3 minus lambda as common outside. So then we will be getting, let us write it over here. And from this we can also see that if 3 minus lambda is the factor, then we can say lambda equal to 3 will be one of the root of this characteristic equation. So it is 3 minus lambda times. Now that will become all ones because we have taken common. The remaining will be 1 minus lambda 1 1 1 1 minus lambda 1 triple 1 minus lambda. So now here we have to apply some transformations and try to get its determinant. So as you can see, there are all the ones in the first row, so that can be used to subtract from the other rows, making them zeros. So what we can do is, let us say R2 equal to R2 minus R1. From all the rows there are 3 ones and in this there are 4 ones. So that will be helpful. If you subtract R1 from every row, R4 equal to R4 minus R1. So let us see what does it give us. And after we get some number of zeros, then we can take its determinant and that would be simpler to handle. So this will become, the first row stays as it is. The second row will become 0 minus lambda minus 1 0 0 0 0 minus lambda minus 1 0 0 0 0 and minus lambda minus 1. So this is what we have got. Now we can take its determinant because there are a good number of zeros and things will get eliminated fast. So when we take its determinant, it will be breaking it on this first row. How do we take a determinant of 4x4 matrix? For, let us say, for this element, we will consider this 3x3 matrix, and similarly for the others in the same row. So we'll be doing 1 times the determinant of this submatrix minus lambda minus 1 0 0 0 minus lambda minus 1 0 0 0 minus lambda minus 1. Then for this one, as you know, we do I plus j thing. So this one will get plus, minus, plus and minus based upon the value of I plus j if it is even or odd for the cofactor matrix. So doing that, when we expand this entire thing and we take the determinant of this, then we will be getting the factor as minus lambda minus 1 the whole cube after solving this entire thing. And here we already have this factor of 3 minus lambda. So this actually is our characteristic equation for the matrix. And as you can see, what are the roots does it have? One of its root is 3 from this, and this is having 3 roots, which are minus lambda minus 1, you will be equating it to 0, and from that we'll get lambda equal to minus 1. So that will be the repeated roots, minus 1 each. So the largest root it is having is 3 itself. And hence we will say that the eigenvalue for this matrix is also the value of its largest root of the characteristic equation, and that is 3 in this case. So its eigenvalue also becomes 3, and that is our answer. This is an engineering mathematics question about exponential distribution. They are saying that the lifetime of a component of a certain type is a random variable whose probability density function is exponentially distributed. So it says that it's about exponential distribution of a probability function and with the parameter 2. For a randomly picked component of this type, the probability that its lifetime exceeds the expected lifetime is to be determined. So now in case of exponential distribution, we say that f of x comma lambda, where this lambda gives us the average probability, which in this case is the average lifetime of a certain component, that is mapped as, if the value of x is greater than or equal to 0, then we say that it is lambda times e raised to minus lambda x, otherwise it is simply 0. So we are concerned with this particular case, and they are already saying that with the parameter 2, which means its average lifetime, they are saying that lambda value here that is given as 2. And in case of this probability function, because it is exponentially distributed, in this we find out that the mean value, it's given as 1 by lambda, which in this case will become 1 by 2 because the value of lambda is 2, so it is 0.5. And we need to determine that the probability of a component whose lifetime is exceeding the average expected lifetime, which means we want the probability of x greater than or equal to, it is simply exceed, so equal to will not be there, it's just strict inequality, probability of x greater than 0.5, that has to be found out. So as we already know, for such cases of exponential distribution, we need to make use of integration in order to find the probability. So how do we do that? We will perform this particular integration, the lambda here and e raised to minus lambda x dx, the lifetime has to exceed 0.5 and maximum it can be anything, so we'll put the upper limit as infinity. So this is the probability that we want to find out. So let us solve it. As we know, lambda is a constant whose value is 2, so let us simply take it outside and we'll perform this integration, e raised to lambda x dx within these limits. So now the value of this integration would be e raised to minus lambda x upon minus lambda. Here we are having lambda, and then we have to put these limits. So both these lambdas get cancelled out. So we are left with minus e raised to, and the value of this lambda we can substitute here as 2. So that is minus e raised to minus 2x. So putting the limits, this will become, let us take that minus outside. When we substitute infinity, it will be e raised to minus infinity, minus of, now substituting 0.5, that will be e raised to minus, then now this is 2 and this is 0.5, so that will give 1. So this is what we get, and we know that e raised to minus infinity tends to 0, so that term is cancelled out. So we are left with minus of 0 minus e raised to minus 1, or it is simply e raised to minus 1, that is 1 by e. So that is our answer. We will now be substituting the value of e and dividing it by 1. So we get the answer as 0.367 and something ahead digits of that. But since we want it to be rounded off to 2 decimal places only, we will be taking the result as 0.37. So that would be our answer. Compiler design question about SDT. We have been given a grammar along with the semantic rules making up this SDT, and we have to identify what this is actually doing, and then based upon that we'll be answering which of the given choices is or are true. It is an MCQ type question, so only one of them would be correct. So let's first have a look at the grammar. It is saying that P derives D star E star. Now here they have not specified what does this star mean. It can be a terminal symbol only unless specified otherwise. So we will be assuming this star to be a terminal symbol itself. And then this D, it derives int of id. Now what does that mean? It records that id.lexeme is of type. It means it is acting as an assertion, and the symbol table is being involved in both of these SDTs. As we know, in the symbol table we have all the information stored about the lexemes, types, and what other symbols we are having. So that is what is being accessed and recorded in these two queries. We can have the lexemes of time either int or bool. So for both of them the separate rules have been given. This one records that id.lexeme is of type bool. So if it is of int type, then that particular entry is made. If it is of bool type, then its corresponding entry is made into the symbol table. And what do we mean by this id.lexeme? Which means the type of that particular lexeme, basically the id1, what exactly it is specifying, whether it's of int type or the bool type, that is what it's recording. Then we have this e derives e1 plus e2, so it is an expression, and in this expression it is first checking that e1's type, this e1 and e2 both are having the same type, that is integer, and then it is setting the type of this e, the result e, as well to be of integer type. Now here, as we can see, the next query is not on the same grounds for bool, so we are only checking the expression which are of type integer. For example, if we have this a and b, let us say 5, 6, both of integer type, then if we have something c equal to a plus b, which is an expression involving addition of two integers, then that is what is being checked in this particular line. If a and b both were of bool types, a equal to 0, b equal to 1, then if we say bool c equal to a plus b, then that would not be validated by it. The next line is this not of even. Now again, they have not specified what does this symbol mean over here, but the rule given is check that the even's type is bool. If not, then set its type to be bool. So it is simply checking the type of boolean variables, but it is not asserting the type of the bool expression, which means if we are having bool a, then it would be passed by this particular expression. It would set the type for it as bool. But if we have a boolean expression, as we just saw above, c equal to a plus b, then such a boolean expression will not be validated by it. Finally, same thing is being done for id as well. Set the type of e as integer, because this id corresponds to something of integer type, so that same type is being assigned to this e as well. So now based upon this, let us see the options, and what we got to know from this, that if we are having arithmetic expressions of the form e equal to e1 plus e2, where both of these are integers, then this particular expression is validated by the grammar. But if they are of Boolean type, then it does not. Boolean expressions are not validated, but Boolean variables are being checked in this particular line. So let's see. The actions can be used to correctly type check any syntactically correct program. Now this any is not possible here. If we are having other than integer and bool types, then it won't be able to type check it or validate it. So this is certainly not true. Then going to the next one, the actions can be used to type check syntactically correct integer variable declarations and integer expressions. So we just saw in this particular line, integer expressions are being validated, and below we also saw that integer variable declarations are also validated. So if we have expressions such as int even equal to 4 something, then that would be validated along with the integer expressions. So this one definitely seems true. Let us also check the other ones. The actions can be used to type check syntactically correct Boolean variable declaration and Boolean expression. Now we saw Boolean variable declaration is to some extent in this particular line, it is being checked, but not the Boolean expressions, because in this line we only have that particular facility for integer expressions. So this one would be incorrect. Then last, the action will lead to infinite loop. The loop is definitely not possible. So both of these turn out incorrect. We'll be going with option B. This question based upon transactions and system recovery. We are having a database system that crashes again while recovering from a previous crash, which means we are facing a crash inside a crash kind of thing. Before we could recover from the first crash, the system once again crashes for the second time. So in this scenario, we have to assume that checkpointing is not being implemented by the database either during the transactions or during the recovery. So in such a scenario, if we are not even having the checkpoints, how will we perform the recovery? So based upon this situation, then we have to identify which of the given options is or are correct. It is an MSQ type question. Let us first understand how exactly this recovery will take place. So as it is given that there are no checkpoints. So without checkpoints, what is the other option we can use for recovering? We can use the system logs, the log records that are stored, and as a result of which we will be performing log-based recovery in this. And what exactly happens in this log-based recovery? In log-based recovery, we have two terms. We can either undo a transaction or we can redo a transaction. When do we undo a transaction? Let us say when a transaction had started, then the crash took place over here, and the transaction had neither committed nor it had aborted. So it has simply started and then this crash happened before it could either commit or it could abort. In such situations, those transactions are to be undone. And when do we perform this redo? When a transaction had started and along with that it had either committed or aborted, and after that there was a crash. So if such scenario happens that a transaction had started and it had completed in the sense either commit or abort, both are allowed. So for such a transaction, if this crash takes place after it has finished, then we have to redo that transaction. So this is how we perform the recovery using system logs. So let us consider an example over here. Let's say we have three transactions, P, Q and R, and let's say all three of them are executing, but P and Q have already committed, or let us say P has committed and Q has aborted. R has done neither of them, and then we face this crash 1. So now after this crash 1, what will happen? We will try to perform this log-based recovery to recover from that. In that, what will we do? We will say redo P and Q, undo R. That is what we will be trying to achieve because P and Q were finished. Using either commit or abort, we'll try to redo them, and R had done neither, so we will try to undo that R. And in the meantime, while we were doing this, the crash 2 takes place. So at this time, what will happen? We will be using the same log records which we were using after the crash 1. So there are no new logs created because all the three things were proceeding with their executions. So we will have to use these same log records again, and just as it is given here in the option 1, the same undo and redo list will be used while recovering again, which means from the second crash. We will again use the same log records, and what do they say? That we need to redo PQ and we need to undo R. So the same thing will be done again after the second crash, and that is how we can perform the recovery. So yes, it is possible to recover from the system. So this option 1 would be true. The second one is saying that we cannot recover any further. No, this is incorrect. Recovery is possible using the log records. So that's wrong. All the transactions that are already undone and redone will not be recovered again. This is again incorrect, because here we are having both the transactions that are already undone and redone. Let us say before this crash 2, assume that this P had committed successfully. If that happens and then this crash 2 takes place, but because we're again using the same log records, what does those log records say? That we need to redo P. So even after this P was committed before the second crash itself, it will again be recovered, will again be redone for the second time. So this option 3 is also incorrect, because we are not actually concerned with what happened between the crash 1 and crash 2. We are only concerned with whatever was the scenario before the crash 1, and based upon that only we are performing the recovery for the second time. So it does not matter which of them actually had redone or undone between them. So lastly, the transaction will become, the database will be in the inconsistent state. This is again incorrect, because when do we have inconsistency in the database? When we have the same variable that is taking 2 or more values in different transactions. Here the thing is, we are not reading or writing anything from the uncommitted transactions. We are simply trying to redo them or undo them based upon the log records whichever were stored before this crash 1 had taken place. So here we don't have any chance of inconsistency, because simple reason is that there is no read write from uncommitted transactions. So the system would be in the consistent state after we perform the recovery from this crash 2. So the only correct answer we have for this one is the first one. This is a C programming question. Which of the following standard C library functions will always invoke a system call when executed from single-threaded process in a Unix or Linux operating system? So we need to consider this always over here, and we have to check for the C library functions from the given options, from them that always invokes a system call. So let us check the options. First one is exit. As we know, it is used for the terminating condition, and it is a library function itself, but internally it always invokes a system call. So this is true, and this was an MSQ question, so multiple can be correct. So looking at the next, that is malloc. As we know, malloc is used for dynamic memory allocation, which takes place from the heap. And let us say you have a process from which you are requiring 100 bytes of memory. So you request a malloc, you call this malloc function with parameter 100, because that is the number of bytes that you want. But internally what happens is that for the first time, this malloc will make a system call to the operating system, and in response to that system call, what the operating system will do, it will provide the memory from heap in some excess than that was requested by the call. So if you're requesting just for 100 bytes, it is possible that the operating system gives you 1 kilobyte, let us say 1024 bytes in return. So what this malloc function will do, it will give you just 100 bytes itself because you had requested that much only, and the remaining would be kept as a buffer. It will be used for the next time. So if you again perform a system call, if you again call this malloc function with, let us say, 200 bytes this time, then first it will check for this buffer that is present in the intermediate layer if any excess memory is available there or not. And here, since it was 1024 and from that you just used 100, so about 900 bytes would still be left there. So these 200 will actually be given from these 900 itself without again making the function call to the operating system. So that means there is no system call involved in this particular case. So in case of malloc, system call may or may not take place always. Internally it uses this BRK and SBRK type of system calls, but they are not always used. They are used only when the available memory in this buffer is less than what is requested. If it is greater than that, then from this buffer itself you are allocated that memory. If not, then the call goes to the operating system, which will allocate you memory in excess than what you had requested. So this malloc does not always invoke a system call. So because we have this word always, we will not consider this to be the answer. Then coming to the third one, that is sleep. Again, this sleep is a function in which we pass the parameter as a time in milliseconds or seconds, and internally it also every time invokes a system call. So this would also be one of the answer. Then the last one, that is strlen. It's a standard function that we always use in the programming, strlen, and then you pass a string object, string parameter into it, and it returns you the length of that particular string. So just for calculating the length of the string, it just needs a traversal and it can return you the length. So there is no system call involved for this one as well. So we saw only exit and sleep. These are the two functions that invoke, that always invoke a system call for their implementation. So the correct choice would be A and C. To the networks question, we have been given these two statements based upon MAC addresses and ARP protocol, and based on that we need to identify which of these statements is or are true. So before that, let us understand what is this ARP. ARP, or we call it an address resolution protocol. It is what we use when we have the IP address and we want to get the MAC address of the corresponding device, which means the device which is having this particular IP address, we want to know its physical address or the MAC address. Then we use the ARP protocol. So there are two states in it, the two phases you can say, the request and the response. What does that mean? In the request phase, what do? We create a packet in which we will be putting all zeros because we don't already know what are the addresses we actually want. So we will request giving the IP that for this IP I want the corresponding MAC. But since we do not know where is it to be broadcasted in the LAN, so to which host it is to be actually sent. So this packet is actually broadcasted in this entire LAN. So the ARP request is a broadcast packet, but when it comes to ARP response, then the particular host, when we have the DHCP or bootstrap kind of protocols being implemented, then what happens is in that LAN, the correct host or that central device, it will be returning us the MAC address for that corresponding IP address. So it is a unicast packet, which means ARP request is broadcasted while ARP response is unicasted. So that's what these statements are saying. the destination MAC address of an ARP reply is a broadcast packet. No, that's incorrect. As we saw, for AIP reply, it is a unicast address being used. For broadcasting, we use the broadcast address of all the ones, but if it is unicast, then we use the appropriate address for that corresponding device itself. And in S2, it is talking about the ARP request, which is definitely a broadcast address. So as we can see, the statement S1 is incorrect, but S2 is true. So we will be going with the third option. S1 is false and S2 is true. So this is correct. An operating systems question based on process synchronization. They have given this pseudocode that is used to perform the synchronization, in which S is a semaphore initialized to 5. So it is a counting semaphore because its initial value is 5. In line number 2, that is here it is being initialized with value 5. And counter is a shared variable initialized to 0 in line 1. So this counter, it's a shared variable, which means for all the processes the same value of counter would be used. They will not have the separate variables named counter for each of them. Assume that the increment operation in line 7 is not atomic. So this is what they're talking about, and this operation is definitely not atomic because it is said that counter is a shared variable. So if it is incremented by one process, then it will be incremented for all of them. That is what they mean by operation being not atomic and the variable being shared. So now this pseudocode is given based on which the synchronization will take place. And at the end, what they are saying, if 5 threads are executing this function concurrently, then which of the following program behaviors can be possible? So it is an MSQ type of question. So let's first understand the synchronization they have used. Initially, the value of this shared variable counter is 0. Then the semaphore is initialized to 5. And here from this line 3 onwards, here is where the parop function starts, and this function is executed by 5 threads, or we can say 5 processes simultaneously. So what does this function do? It is using 2 weights on the semaphore. Initial S value is 5. So whenever a process wants to enter the critical section, it will first perform 2 weight operations, which means it will decrement the variable S, semaphore S value by 2. And after that, it will enter the critical section that has not specifically been mentioned. And after that, when it is done from there, it will increment the value of this shared variable counter by 1. And before leaving, it will once again perform 2 signal operations to restore the value of the semaphore S. So this is how the synchronization works. Let us check out what are the given options. The value of counter is 5 after all the threads successfully complete the execution of parop. Now this parop is this particular function that's being executed by the 5 processes who are trying to execute concurrently. So is it possible for the value of this counter to be 5 at the end? It is possible if all of them execute sequentially, one after the another. Let us say the 5 processes are A, B, C, D and E. So first this A will execute, initial value of counter was 0, so this A will make it 1, then it will complete its execution and come out. Then B will start executing this parop function, so it will increment the counter variable value to 2, then 3, 4 and 5 at the end. So yes, it is possible that at the end value of the counter variable would be 5. It's possible if sequential execution is performed. Now the second one is saying that its value can be 1 after the execution. Now if they execute sequentially, then it is definitely not possible. So let us see if it is possible if there is some interleaving between them. Let us say the first process A, it starts executing this parop function. It completes its line 5, line 6, but when it is at this line 7, at that time what happens is it has to increment the counter variable, and we know that this increment takes place in 3 steps because we need to use the register for this purpose. So first it will read the counter value, then that value would be incremented and stored in the register, and after that it will be written back to the, it will read back from that memory, from that register. So these are the 3 steps in which increment actually takes place. But let us say when this process A was on this line 7, and while it was performing this increment operation, the counter plus plus operation, at that time itself another process, let us say this process B came into picture, and this process A got it went into the waiting state, that it got preempted there. It would go into waiting state. It would, let us say this was line 1, 2 and 3. It had incremented the value in the register, but this return back operation was left. So when it again comes back from its preemption, then it will resume here at line number 3 of this operation. So let us say in the meantime, until now the counter value is 0 itself and A is in the preempted state. Let us say in this meantime B, C, D and E, all of them execute sequentially. So what they will do, they will increment the counter as 1, 2, 3 and 4. So now final value of counter is 4. But now when all of them are done, then this processor comes back and it resumes here at its line number 3 of incrementation step. So now only return back was left. The value was already changed from 0 to 1 because when it read the counter value it was 0. So it changed it to 1, and just what was left was it had to write back that 1, which means now after resumption what it will do, it will change the counter value to 1 from 4. E has made it 4, but this A will once again make it back to 1 and complete its execution. So at the end, as we saw, it is possible for the counter value to be 1. Now option C is saying the value 0. 0 is definitely not possible, as you can visualize that in whichever way do we execute the processes parallelly, sequentially, with interleaving, with preemption, it is never possible to get the value as 0 because whichever process executes last, it will definitely increment it from its previous value. So 0 is not possible. And the last one is saying there is a deadlock involving all the threads. Now in this scenario, is the deadlock possible? Let us say we have every process performing 2 wait operations. So if it so happens that because we have the initial value of S as 5 and we have 5 processes as well, then what if all the processes start concurrently, all of them reach up to this line 5? That means all of them perform 1 wait operation on this semaphore. So when all the 5 of them have completed their line number 5, at that time the value of S would have become 0. After that, no process can move on to line number 6. Means all of them are struck at this particular point. They are waiting for the semaphore, but its value is 0. So this is where a deadlock will take place. None of them can move ahead and none of them can even release their held resources. That is, none of them can perform a signal operation after this 1 wait. So if such a thing happens, then it would lead to a deadlock. So it is possible to have deadlock when all the 5 processes acquire 1 wait operation on the semaphore each. So option D is also true. So we got A, B and D as our answer. This is a compiler designing question based upon LL1 parser. we have been given the following context-free grammar having these rules, and the set of terminals here is A, B, C, D, and F. We have also been given this LL1 parsing table, which is incompletely filled. There are these 1, 2, 3, and 4, which we have to fill, these 4 productions, and other than that, the entries are made in it. So what do we would be filling in these blank cells? That has to be determined. So for that, this is our given grammar, and in order to create an LL1 parsing table, for that first we need to find out the first and follow of all these non-terminal symbols. So we have created this first and follow table over here. As we can see, for S we have in the first D, C, and F, these. And how do we get them? As we can see here, in the first of S we have this D, and also the first of S will be first of R. So we go to R, and here we see C comes from this, so D and C, and also R can derive epsilon. So if R gets epsilon, then this next F is there, that will be taken. So we get D, C, and F as the first of S. Then coming to T, in first of T we will have this A from here, B from here, and it is also deriving epsilon, so that will be there, A, B, and epsilon. Next, coming to R, it is C and epsilon, because it derives C here and epsilon as well. So we have got first entries for all the 3 non-terminals. Now coming to the follow side, let us start with R first. What do we say is the follow of R? Here we have this F. Other than that, there is nothing to be placed in the follow of R, so it will simply be F over here. Then coming to S and T, there are these 2 productions. For S we can see that here we are having this R, so corresponding to R we will have those entries. Follow of S will be taken from R as well, so because F is there in the follow of R, so that will be included here. And because S is the start symbol, so the dollar sign will also be there, indicating the end of the string. And also this C comes from here, because we have this R here, so S will also have the symbol C in its follow. So we get CF dollar sign. And when we are dealing with the follow of S, follow of T, because here we are having the S, so we will say that follow of T will be the same as follow of S. And hence we get the same entries CF and dollar in the follow of T as well. So we have created this first and follow table. Now based upon this, we will be going for the LL1 parsing table that has been given here incompletely filled. So let us check out. For the productions, let us see, S derives, okay, it's better if we clear this out. Alright, so the first production we have is S derives DAT. Where should this be placed? In the first of S, but here the start symbol is D. So this particular production S derives DAT will be placed only under D. Why so? Because here the start symbol which is included in the first of S is D itself. And as we know, there are other 2 symbols present in the first of S as well, C and F, but both of them are associated with R. So under them, this particular production S derives RF has to be placed. So for this particular cell S and C, the entry would be S derives RF, and same goes for position 2 as well, S derives RF, that will be placed. Then coming to T, this is the first production, T derives AS, so this will be placed under A, and that is already given. Then next is T derives BAT, that will be placed under B, it has already been placed in the table. Then comes T derives epsilon. Now we know that whenever there are epsilon productions, then those are placed in the follow of that particular non-terminal. So what do we have in the follow of T? We have C, F, and dollar. So under each of them, the production T derives epsilon will be placed. It is already given under F, so we will be placing it under C and under this $sign. T derives epsilon. So all the four are already done. Let us also check for R. This production R derives CATR, that will be placed under C. It's already given. And the next one, R derives epsilon, will be placed in the follow of R, that is F. So under F, this R derives epsilon will be placed. It's already been given. So we have found the entries corresponding to all these 1, 2, 3 and 4. For 1 and 2, we have got S derives RF, while for 3 and 4 we have got the same entry, T derives epsilon. So let us see which of these options matches. S derives RF, S derives RF, T derives epsilon and T derives epsilon. So the matching option is first one. So we'll be going with option A. Policy question based upon DFAs. We have been given this particular language L, where we have W belongs to 0, 1 star. This is actually the closure of 0, 1, such that W ends with the substring 0, 1, 1. So we can map this particular language with this regular expression 0 plus 1 star followed by 0, 1, 1. So this is our language L, and for this language we need to identify which of the given DFAs is correct, or which of them correctly represents this particular language or accepts this language. So let us have a look at the options. This is the first one, in which we have 0, 1, 1 over here, but we need to check if our strings are ending with 0, 1, 1. But here we can see in the last state there is a loop for 1. So this DFA will also accept the string something like 0, 1, 1 and another 1 because of this loop. So this is not allowed because we want our strings to be ending with 0, 1, 1. In this we just have a substring 0, 1, 1. So this one would be rejected. Then coming to option B, again we here have 0, 1, 1 as a substring, but are our strings ending with 0, 1, 1? Here again we can see there is a loop in the last state. So it will also accept the strings in which there is the 0, 1, 1, but after that we can have anything. So it is possible because of this loop that we accept a language like 0, 1, 1 and followed by any number of zeros. So that is a contradiction because this particular string does not belong to our language. Then coming to the next option, in this one again we have the substring 0, 1, 1, but let us check if it is ending with the substring. Let us call these states as 1, 2, 3 and 4. So as we can see, there is a loop for 0 in this state 2, and after that here we have 1. From 2 to 3 there is a transition for 1, and in this state 3 if we get any 0 then we are looping back into the state 2. So this will ensure that after a 1, 0 will not be allowed. We want a 1 after that. So we are looping back, and here the second one is completed in the state 4, and after that if we get any 0 then we are moving back by this particular transition. We are going back to state 2 so that every 0 here will be followed by a 1, 1 if it has to be a ending substring. Similarly, if we get a 1 in this particular state, then it is going back to state 3. But this is the transition that will cause problem. Why? Let us see. Because of this particular transition 1 from state 4 to state 3, what will happen is, once we get the substring 0, 1, 1, after that it is accepting even number of ones. We get 0, 1, 1. Currently we are in the state 4 and we got another 1. So we came back to the state 3 with another 1, and from now the state 3 we can go back with a 1 to the accepting state, that is state 4. So this string has got accepted. which should not have been the case because here the ending substring is not 011. So both B and C are also rejected. Then coming to the last one, obviously it has to be true, but let us check out. Here we get the substring 011, and after that, from this last state, if there is any 0, then we are coming back to second state, so that this 0 again gets followed by 11. And from the accepting state itself, if we get a 1, then we are transitioning not to the state 3 but to the starting state here, so that once again here at this particular place, if we get a 0, then again 2 ones have to occur. That's why we went to this particular state 2 using this transition. But here itself, if we had got a 1, then we again need to repeat the entire 011 thing. That's why this transition is taking it to the start state, so that once again 011 can be repeated, and that forms the ending substring for the language. So we see that option D is the correct answer. CI question based on a pipeline processor. We are having a 5-stage pipeline which is having the stage delays of 150, 120, 150, 160 and 140 nanoseconds respectively for the 5 stages. And it is having registers that are used between the stages, and each of them has a delay of 5 nanoseconds. So this will involve our buffer delay. And we have to execute 100 independent instructions on this pipeline processor such that there are no stalls involved. So in this scenario, what will be the total estimated execution time for these processes that has to be evaluated? So first of all, let us note down what all values we have been given. It is a 5-stage processor, so we denote that by K equal to 5. The number of processes to be executed is 100, so we write N equal to 100. And now the total delay has to be calculated for the stages. We are having 5 stages, each of them is having different execution time given. So if we look at the one which is maximum among all these 5, then it would also involve the other ones. For example, since this is a pipeline processor, so if I'm executing 2 processes in this, one is having a delay of 20 nanoseconds, other is having 10 nanoseconds, and both are executing parallelly. So by the time this bigger process would have finished its execution, the smaller one would also have been completed. So we look for the one which is having the maximum delay among these 5 stages. Which one is that? 160. This is the stage 4, and that is the most time consuming stage. So by the time the process is out of this stage, the others would have also been incurred for. Hence, the total delay would be given by 160, which is the maximum of all these 5 stages. That will be responsible for the delay. And to this, we will need to add if there is any buffer delay involved. We have already been given that there are registers which will incur buffer delay, and its value is 5 nanoseconds. So our total delay becomes the maximum for all these stages plus the buffer delay, which is 165 nanoseconds. So now we have got all the values, and we can simply calculate the execution time in a pipeline processor, which is given as K, which is the number of stages, plus N minus 1. N is the total number of processes to be executed, and that multiplied with the total delay. And how do we get this expression? In a pipeline processor, the time taken by the largest one, this is the largest process, and at this point of time this process is completed. So now in every second we will have one more process completing its execution. So that is how we get this formula. You can check out the derivation, it's quite simple. And we can substitute the values in it to get 5 plus N is 100, so N minus 1 99. That multiplied with the total delay, which is 165. So we get 104 times of 165, which is 17160. So it is approximately 17,000 nanoseconds. That is the unit they require. And this is the total execution time for all the given 100 processes in this pipeline processor. So that is our answer, 17160. This is a COA question from caching. We have been given a computer system with byte addressable primary memory of size 2 to the power 32 bytes. So the main memory size has been given to us as 2 to the power 32 bytes. The computer system has a direct map cache of size 32 KB. So the cache size is 32 KB, which we can write as 2 to the power 10 and 5. So 15, 2 to the power 15 bytes. Each cache block is of size 64 bytes. The block size is 64 bytes, or we can say 2 to the power 6 bytes. We have to determine the size of the tag field in this cache. Now it is a direct map cache, so the structure would be like the tag bits at first, then the lines, and at the end we have offset. What would be the offset in this case? The main memory size is given as 2 to the power 32 bytes and the block size is 2 to the power 6 bytes. So offset is the number of bits required to represent a block. So that would take 6 bytes. And because our main memory address is of 2 to the power 32 bytes, this entire physical address will have 32 bits, because that is the number of bits required to represent this address. So out of these 32, 6 are done for offset. Then we are left with 26 bits for tag and lines combined. Now, what is the number of lines? Lines is given by the cache size upon block size, which means what is the number of lines or what is the number of divisions that particular cache is having. So that would be 2 to the power 15 bytes, which is the cache size, upon 2 to the power 6 bytes, which is the block size. And we assume that the block size is same for both the cache memory as well as the main memory. So this becomes 2 to the power 9. There will be no unit because both the units get cancelled out. So there will be 2 to the power 9 or 512 lines in this direct map cache. Hence, the line offset will take 9 bits. So now we are only left with the tag field, and these 26 bits were left for tag and lines combined. Out of those, 9 bits are taken by lines. So tag will occupy 26 minus 9 equal to 17 bits. So in this direct map cache, the size of the tag field will be 17 bits. That is our answer. This is a graph theory question. We have been given a graph G, which is undirected, unweighted and connected. And for this graph G, they are defining its diameter as the following expression: max of u comma v element of v, means there are two vertices u and v taken from the vertex set of this graph G. So for that, what are they taking? The max of length of shortest path between u and v, which means we will take up every possible pair of vertices from the graph, and between those two vertices we will find out the shortest path, and among all the shortest paths we get, we will take the maximum one. For example, let us consider this particular graph. It is having 5 vertices and it is all undirected, unweighted as well as connected. So in this graph, if we consider the vertex set A and B, then what is the shortest path between them? It is simply A to B, and its length is 1. So we got 1 over here. Now let us consider E and C together. So between E and C, what is the shortest path? There are two paths, EABC and EDC, but we'll go with the shorter one, that is EDC. The length of this path is 2. So we have got the next shortest path is as 2. Similarly, if we take any other pair, let us say A and D, again we will get 2. And if we take any adjacent vertices, then we will get 1. So for this graph, what is the maximum that we are getting? It is 2. So between any two vertices of this graph, the maximum length of the shortest path between those two vertices is 2. Hence, for this particular graph, the diameter will be 2. So now what do we have to do? They have said that M is the adjacency matrix of G. So for the graph which is under consideration, M is its adjacency matrix. And now they're defining a new graph G2 on the same set of vertices with adjacency matrix n. So there is another graph G2 having adjacency matrix as n. And how is that n defined? It is defined as 1 if Mij is greater than 0 or Pij is greater than 0. What is this Mij? It is an element of the adjacency matrix M. And what about Pij? It is an element of the matrix P, where P is defined as M squared, which means we will have a graph G. Corresponding to it, there will be an adjacency matrix M, and we will multiply it with itself, M cross M. That will give us P, which is nothing but M square. Then using both M and P, we will construct a new adjacency matrix that will be N, and this N will correspond to the new graph G2. So that is what they are saying. If Mij is positive or Pij is positive, then Nij will be 1, otherwise 0. So now what do we have to do is, first we have to get this matrix N, and then using that matrix we have to construct this graph G2, and then they are asking us about the diameter of that new matrix G2. So how will we approach this question? If we try to do it theoretically, then it would be difficult to visualize, so we can better take some examples. But the thing is, we cannot consider bigger graphs, because if we had taken the same example, then it is a 5 cross 5 adjacency matrix that will be resulting out of it, and handling such big matrices would be difficult. So we would go with graphs with just 2 or 3 vertices. So we have considered this particular graph. There are other choices such as this graph, or simply with 2 vertices, or a disconnected graph with 2 vertices. So those are the different choices we can have, and we can perform the same operation for all of them and verify. So let us do it using this particular graph. So here we can see it is having 3 vertices, A, B and C, and this is our graph G. What would be the diameter for this particular graph? If we consider A and C together, then this is the shortest path between them, which is having a length 2. So for this graph, the diameter will be 2. And what will be the adjacency matrix for this graph? That is given over here as M. A, B, C are taken in the rows and columns, which are vertices, and then they are 1 if there exists a path, direct path between those 2 vertices, otherwise it is taken as 0. So we have constructed this matrix M, and then multiplying M by itself will give us M squared, or what we call as P. That has been already created over here, and we get the entries in it as 101, 020 and 101. So now we have got both M as well as M square, that is P. So using them, now we can construct the new adjacency matrix, that is N. And how will we construct this one? For every corresponding element, we will check if either Mij is 1 or Pij is 1. So for this first element, we got 1 from this P. For the next one, we got from M. For third element, again from P. So as it can be seen, there are 4 ones in this M that contribute to the corresponding ones in N, and there are these other 4 ones over here. And what about this 2? It is said that it must just be positive, not necessarily 1. So even if we are getting a 2 from this Pij corresponding to B and B, which means P BB is 2. 2 is greater than 0, so it will imply that N BB will also be 1. And that is how we construct this entire graph, and it turns out to be all ones. So this is the adjacency matrix that we have got corresponding to the graph G2. And now looking at this, what can we say about G2? What kind of graph will it be? Every node is connected to every other node in this. So we can call such graph as a complete graph. If we construct this particular graph G2, then it would be something like this. A, B, C, and also there are kind of self loops because A to A, B to B, and C to C are also connected, and every node is connected to every other node. So for this particular graph, what can we say about its diameter? If we take any two pair of vertices, A, B, B, C, or AC, there is a direct path between them. And that is the shortest path itself, having a length 1. So diameter of G2 will also become 1. So what did we get? For G, diameter was 2, and for G2, diameter was 1. So now, considering this, let us have a look at the options. First one is saying diameter of G2 is less than or equal to ceiling of half of diameter of G, which means 1 less than equal to half of 2, that is 1, and ceil of 1, which is again 1. So 1 less than equal to 1. Yes, it is true. Let's also check other ones. This one is saying half of that, means 1 less than 1. This is wrong. Third one is diameter of G2, that is 1 equal to diameter of G2. This is also incorrect. And similarly, the last one, it is saying 2 less than 1. That is wrong as well. So we will be going with the first option. In the same way, we can take any other graph having less than or equal to 3 vertices and verify for that as well, and we will be getting the same result. So the correct answer for this question would be the first option. Algorithms question. We have been given an undirected graph having this edge weights as shown in this figure. We have to determine what would be the number of minimum spanning trees existing for this graph. Now, since we can see that all the edge weights are not distinct, so it will definitely have more than one spanning trees. But how many? For that, we can apply either Kruskal's or Prim's algorithm and determine what is the result we get. Let us go ahead with Kruskal's algo. We have these 9 nodes. Let us denote them here. Right. And there are only 2 different edge weights, as we can see. It is 0.1 and 0.9. So let us start with this vertex, and we will be following Kruskal's algo. So we'll keep adding the edges with minimum weight such that they do not create a cycle. So here we'll start by including this edge first, having the weight of 0.1. This edge is included. Then we can go ahead with this one, 0.1. Now in this upper component, there is no other edge having the minimum weight of 0.1. So now we'll go for the lower component, and we can include either of either of these 4 edges. All of them are having weight 0.1. So we'll include all 4, seeing that they do not create a cycle, which they will not in this case. There are 5. This middle one is also there. So all of those 5 edges will be included in our MSD. So we have reached till this point, and now there is no edge left having weight 0.1. So we only have these 3 edges left, which are having the weights 0.9 each. But as we can see, our MSD is still having 2 different components, and they will need to be connected to each other. And we are having 9 vertices. So what is the number of edges we'll need to have? So 9 minus 1, which is 8. And how many we have already had? 7. 1, 2, 3, 4, 5, 6, and 7. So we just need one more edge that will connect these 2 components together. And how can we do that? We'll select, we are having 4 options, these 4. But if we add this edge, then it will create a cycle, so it won't be anyways included. So then out of these 3, we will include any one. We can have either this is an MSD, or we could have in place of this the middle one. This is also an MSD. Or instead of this, we could have had the last one. All of them are possible. No cycle would be created. The 2 components would be joined to each other, resulting into an MSD. So we are having just 3 different options that we can choose any one of these 3 edges. For others, there is no option. All the edges having weight 0.1 will definitely be included. We just have an option among these 3. So there are 3 different MSTs possible for this graph. So answer would be 3. TOC question. We have been given this M that represents encoding of an automaton M. It is not given what type of automata it is. Suppose that the language set sigma is between 0 and 1. So which of the following languages is or are not recursive, that we need to determine. So looking at the first one, L represents encoding of an automaton M such that it is a DFA such that L of M is theta. Now what does this imply? It is a language, M is a DFA actually, whose encoding we are dealing with, and this DFA accepts nothing. So, and in the same way, in the second one also we have M, which is a DFA, but there the language accepted is sigma star. There L of M is sigma star, this way it is. So as we know, this sigma star being implied by the language signifies the completeness problem, and this is the emptiness problem, that the language accepts nothing. And what type of automata is M in this case? It is a DFA, which means a finite automata that deals with regular language. And we know that for regular languages, or for that sake finite automata, the regular grammar, in that one both the emptiness as well as the completeness problems, both of them are decidable. We can cross check that in the decidability table that we have, and we come to know that both of these type of problems are decidable, and this decidability implies recursiveness. Because if this problem is decidable, then we can have the corresponding recursive language for that. So we get that both options A and B that represent recursive languages. Then coming to the third one, there M is a PDA. It is representing the push down automata such that again L of M is theta. So in this case we have a PDA which will correspond to the context free grammar that have corresponding context free language. But here we will consider just CFL and not DCFL, because the determinism is not guaranteed for this case. We are dealing with this emptiness problem over here. In case of CFL, the emptiness problem is decidable. So this language also becomes recursive. But then looking at the last one, there also we have PDA, but the problem under consideration is this completeness problem. And as we know, the completeness problem, it is decidable only for DCFL, but if we consider CFL, then completeness problem is undecidable. And what does undecidability imply? It implies that the language will either be non-recursive or it will be recursively enumerable. So what do we get? It is definitely not recursive. And what can it be then? It can be either non-recursive or recursively enumerable. So this is the one that satisfies the given condition that the language under consideration here is not recursive. So we'll be going with option D over here. Now file systems question from the operating system. They are saying that we have a linear list based directory implementation in the file system such that each directory is a list of nodes where, so let's say we have this directory in the form of nodes, and each of these nodes represents each directory is a list of nodes. So this is our directory, let's say 1, and it is a list of some number of nodes, and each of these nodes, it contains a file name along with its metadata. So this is the implementation of the file system that is being followed in this particular operating system. So what they are saying now, such as the list of pointers to the data blocks. So what these nodes are actually, they are storing the name and the metadata, which will include the pointer to the actual location where that file is present. These nodes don't represent the actual files. They have the pointers to the place where the contents of the file are actually stored. So this is the directory structure that has been given, and for this directory foo, there is one particular directory called foo. So for this particular directory, let us call it foo, and for that particular directory, they are asking which of the following operations will necessarily require a full scan for the successful completion. So this foo is a directory that is arranged in the form of a list of nodes like this. It is kind of a linked list data structure, and every node is having the name of the file along with the metadata, including pointer to the actual file location. So this is how our foo looks like, and in this, let us check what are the operations given. Creation of a new file in foo. So for this, we need to understand that in one particular directory, no two files can have the same name. Their names have to be unique. So this property has always to be followed. And now if we want to create a new file, then what can we do? We can simply create a new node and attach it at the start or at the end of the linked list, right? But we will need to make sure that whatever name we are assigning to this particular file does not already exist in any of these. The unique name property has to be followed. So if we want to insert this node A, then we will have to traverse this entire list and check if the file name is already existing or not. So this will require the complete scan. And this was MSQ type question, so multiple can be correct. Let us also check the next options. Deletion of an existing file from foo. Now let us say we want to delete a file named E. So for that we will need to traverse until we find E. At this point we find E, we will delete it. But let us say we wanted to delete just B, so we can directly delete it without any traversal. So this operation may or may not always require the traversal. The earlier we find that particular file, we will delete it, and then whatever, let us say this is our file, we found this is our directory structure, and in that we found this particular node corresponding to the file that is to be deleted. So we will traverse only up to this point and not after that. So this deletion operation may not always require the complete scan, and they have said will necessarily require. So that is not always true for this. So it will be incorrect. Then the next one, renaming an existing file. Again, for renaming, we will need to follow this particular constraint that the names have to be unique. So if there is one particular file D and I want to rename it to A, then I will need to traverse the entire directory named foo and check if there is already existing a file with the name A in it or not. So again, this operation necessarily requires a complete scan, because after scanning all the nodes only, then we can decide whether that particular rename operation can be done or not. Then coming to the last one, opening an existing file in foo. So now again, for this operation, it does not have any constraint involved in it. Just like the deletion operation, there is some file that we will be locating, and as soon as we find it, all the files after that will not be traversed. So we will traverse only up to a certain point until we find that particular file that has to be opened, and after that we will not traverse, we will skip that part. So here in option 2 and 4, only partial traversal may be required. In some cases complete traversal may also be required, but this necessarily required condition is failing for them. So we will be only going with the options first and third. This is a recurrence relation problem. We have been given this particular relation T of n, that is defined as T of n by 2 plus T of 2n by 5 plus 7n for all positive values of n, and otherwise when n is 0, then T of n is taken as simply 1. So for this particular recurrence relation, we have to determine its complexity. So for this, how can we proceed? Using the recurrence tree method, that would be the easiest one. As we can see, the size of the total problem is 7n. So we start creating its recurrence tree in this way. It is divided into two parts, T of n by 2, which means 7 times of n by 2, plus T of 2n by 5, which means 7 times 2n by 5. These are our levels, level 0, level 1, level 2, and so on. Our tree will be constructed. Then from this 7n by 2, it is again divided into 2, t of n by 2, which means 7 times n by 2 squared. And t of 2n by 5 means this thing will simply be divided by 5, making it 7 times of 2n by 10. So this is how we will construct the tree, and at every level we find out the total cost. For example, at level 0 it is simply 7n, but at level 1 we will sum these up. 7n by 2 plus 14n by 5, we will take the LCM and add them up, and then we will be getting 7 will be taken as common, so it results into 7 times of 9 by 10, and that is shown over here. Similarly, if we take the total size of the problem at level 2, it turns out to be 7 times of 9 by 10 squared n, and so on. Now the thing to note over here is, what are the two sizes of the subproblems that we have? It is n by 2 and 2n by 5. These are the two sizes into which n is being divided at every level. But out of these, we can see n by 2 is greater. So if we want to find out the upper bound and the lower bound for this problem, then the upper bound would be given by the larger one, while the lower bound will be given by the smaller problem. So as we can see, if n by 2 is greater, and this n by 2 corresponds to this leftmost subtree of this recurrence tree, and similarly this 2n by 5 corresponds to the rightmost subtree, because in the leftmost subtree all the problems are being divided by 2 every time. It is 7n by 2, 7n by 2 squared, 7n by 2 cubed, and so on. And similarly on the right hand side, the problem is always being divided by a factor of 2n by 5. So what we will be doing is, for calculating the upper bound and for calculating the lower bound, we will be using the leftmost subtree and the rightmost subtree respectively. This upper bound will be determined by the leftmost subtree and lower bound will be determined by the rightmost subtree. This is for the lower bound, and then using both the upper bound and the lower bound, we will estimate what is its exact time complexity. So for that, we will need the height of this leftmost subtree and the rightmost subtree. So as it can be seen, in this leftmost subtree, the problem is being halved every time. It is being divided by n by 2. Partitioning is being made. So the height of this leftmost subtree would be given by log of n to the base 2. And similarly on the right hand side, the height of the tree will be log of n to the base 5 by 2. So we have the heights of both the left subtree as well as the right subtree. So now we can go for calculating the upper bounds and the lower bound. Let us see how that can be done. Starting with the upper bound for this problem, that will be given by this leftmost subtree. We will be adding up all the values we encounter on that path in this way: 7n plus 7 9 by 10n plus 7 9 by 10 squared n. But as you can see, this will proceed up to the number of levels in the tree, and number of levels is same as the height of the tree, that is given by this particular expression log n to the base 2. So this thing will proceed up to 7 times 9 by 10 to the power log n to the base 2 n. So this is what will give us the upper bound. So we will say that t of n is less than or equal to this particular expression, because it is giving the upper bound. And when we calculate this thing using the geometric progression, it will give us 70n minus a particular term in the geometric expression when you apply the formula 1 minus r raised to n plus 1 upon 1 minus r. So this thing will be something positive, and 70n minus of something, which means it is almost, as it can be seen, t of n can be written as big O of n. The upper bound is found to be linear from this. And on the same grounds, when we look for the rightmost subtree for calculating the lower bound of this tree, Then what we'll be doing is we'll say T of n is greater than or equal to, the expression would be same except that the last term would be replaced over here. This 2 will be replaced by 5 by 2 because that is the height of the rightmost subtree. The geometric progression found here is same, just the last term is different. So for this we will say T of n is greater than or equal to this particular expression 70n minus some expression. So again it turns out to be T of n equal to, now this was the case of lower bound, so we will be using omega of n. So we have got both linear, upper bound is big O of n, lower bound is omega of n. So combining both of them, we can say that the average case complexity of it can be said to be the theta of n, linear complexity for this problem. So for this one we will be going with the third option, that is linear time complexity theta of n. This is a combinatorics question from mathematics. We have been given 6 jobs with distinct difficulty levels. So we'll consider that all these 6 jobs are distinct. And there are 3 computers with distinct processing speeds. So these 3 computers are also distinct. Each job is assigned to a computer such that the fastest computer gets the toughest job. Now it is defined that the 6 jobs are distinct and the 3 computers are also distinct. So out of these 6 jobs, 1, 2, 3, 4, 5 and 6, the most difficult job, let us say it is the first one, and this is our set of computers. There are just 3 computers, 1, 2 and 3. It is said that the fastest computer gets the toughest job. Let's say the computer 1 is fastest. Since they are all distinct, there would only be one fastest computer and we need not choose it like doing 3C1. Because all of them are distinct, there would be only one way of choosing the fastest computer. So let us say this is the toughest job that is mapped to the fastest computer. And the slowest computer gets the easiest job. This job 6 is the easiest one, which gets the slowest computer. So now we have 4 jobs left out and 1 computer left out. For these, what we need to do is we have to assign every process a computer such that each computer gets a job. Means there is no vacant computer and also there is no process that is left unassigned. Each process gets a computer and no computer is left unused. So what is the number of ways of achieving this thing? Now we might think of one approach which would be incorrect. Most of us would be going for that in the first case, which is we are having 4 computers and 4 processes and 3 computers. So why don't we simply do it like we will select, each of them has to be mapped. All 4 of them would be consumed, none of them is to be left out. Similarly here, none of the computers would be left empty. So why don't we select 3 processes out of this, give them 1 computer each, and then for the 1 remaining process, we'll allot it any one of the 3 computers. This is what approach you might come up with, that is 4C 3 ways for selecting 3 processes out of these 4. And for those 3 processes, we will allocate them these 3 computers in 3 factorial ways. Now, 1 process would be left out in here because we chose just 3, so 1 is left out. So that 1 process would be assigned to any one of the 3 computers in 3 ways. This gives us the result 6 into 4 into 3, which is 24 thrice 72, and that is incorrect. The reason being, on these 4 processes we applied the selection twice. First we selected 4C3, 3 out of 4, and then 1 was left out. For that we again made a selection for these computers. See, we did 4C3 and 3C3 for the 3 computers and allocated them in 3 factorial ways. Then 1 was left out. For that one, what we did? 1C1, 3C1 and just 1 way. So actually we made 2 selections from the same set. So that involves double counting. Hence this is the overestimated result we got, and that is incorrect. Most of us would go with this on the first side. That's wrong. So what is the correct approach? Let us check out. We will be going with the set theory approach in this case instead of the PNC approach. What we can do is, see, we are having these four processes can be considered to be one set, and all of these three computers would be considered to be one set, not just the middle one. See, there are three computers. This is the fastest one, this is the slowest one, and this number 2 is the middle one. So the processes 1 and 6 are done with. They do not need to be supplied to any other computer. So we now just have to allocate these four processes to these three computers. So it will actually be finding out the number of onto functions from the set P for processes to the set C for computers, because none of these four has to be left out, none of these three has to be left out, and each process will get only one computer. One computer may get multiple processes. So this satisfies all the properties of an onto relation. So basically an onto relation from a set with 4 elements to an onto relation on a set with 3 elements, but with a twist. Let us check out. In case 1, what we can do is, let us say each of these 4 processes is free to choose any of the 3 computers. So the first process has 3 choices, second has again 3, third has again 3 choices, fourth has also 3 choices. So this becomes 3 to the power 4, which is 81. But in this, again, we have made some overestimation, because it is possible that all of the 4 processes would have selected just one or just 2 of the 3 PCs, the 3 computers. Then this condition would fail, that every computer gets a job. If all of them map to just the first one or just the first 2, the last one is left out, that won't be allowed. Yes, it is true that the third one initially has had the process number 6 allocated to it, but what if all of these 4 map to just this middle computer, or all of them map to just the first one? Then this middle would be left out empty. So what now we need to do is, we will be subtracting those cases in which the middle computer is left out, and all of the 4, let us say 2 of them map to PC number 1, and these 2 of them map to PC number 3. This one is left out empty, it didn't get any process allocated to it. So these cases will be subtracted. Which cases? When all the 4 map to just 1 and 3, second one is left out. So how will we calculate that? What we'll be doing, we'll consider that this set is having just 2 elements, 1 and 3, and all of them are mapping to them. So that will have each process now having 2 choices. 2 for process 2, 3, 4 and 5. Each of the processes has 2 choices among PC1 or PC3. So that gives 2 to the power 4, which is 16 ways. So there are 16 ways in which this middle computer would be left out empty. Now we do not need to worry about those cases when the first one or the third one is left out empty, because they already have the fastest, the toughest and the easiest processes respectively allocated to them. So we are only concerned with those cases when the middle computer is left out empty. So we subtracted those cases. There is no other case that needs to be subtracted. All of the constraints have been satisfied. So what is the final answer that we get? The total case is 81, and from that we are subtracting these 16 cases when middle one was left out empty. So our final answer is 81 minus 16, which is 65. So there are 65 ways of achieving the given task. An algorithms question. We have been given this particular array and they are asking which of the following sorting algorithms will use the least number of comparisons for sorting the given array. So we have been given these 4 sorting algorithms, and this is the array which has to be sorted. using these algorithms and have to determine that which of them will use the least number of comparisons. So as we can see, this array is already sorted. So in this case, when an array is already sorted, these algorithms will behave in a different way. Let us see for everyone. The first selection sort, what it will do, if the array is already sorted, it will give the worst performance. In the first pass, it will make n-1 comparisons. Then in second pass, it will make n-2 comparisons, and so on. So the total number of comparisons would be order of n plus 1 by 2 kind of thing, and this is just equivalent to order of n square, which is also its time complexity, because in the sorting algorithms we determine their time complexity based upon the number of comparisons that they use. So for selection sort, we can say its time complexity or its number of comparisons is of the order of n squared. So that is definitely not the least, because the other algorithms may perform in a better way. Let's see how. Then coming to this merge sort, it does not care if the given input is sorted or unsorted. So for that, it will not matter if the array is already sorted. It will still take n log n number of comparisons, and that would be its complexity as well. So for merge sort, the order of comparisons is always n log n, however the input is, given that its size is n. Finally, coming to insertion sort, now this will give a better performance if the array is sorted, because let us take this example 23, 32, 45. Let's say there are just 3 elements. So what insertion sort actually does, it will pick up an element and it will check if the left part of it, let's say we're at currently 32, it will check left part is already sorted. So what insertion sort basically does, it finds out a correct place for an element and goes and places it there. If we get the next element as say 30, then what it will do, it will check this left half which is already sorted, and it will see that this is the correct position for 30. So it will go and insert 30 over there. So 23, 30, 32, 45. This is how insertion sort works. This array is already sorted. It will not need to do any such insertions over there. So it will simply keep checking if there is any violation. 23, 32, 45. If it finds a violation, then it will go and find the correct place for that. But it will not find any. There will simply be n-1 comparisons, and it will reach the end of the array, concluding that it is already sorted. There is no need to perform any swaps. So this insertion sort, it will take order of n comparisons and 0 swaps. So till now this gives the best performance. Its complexity as well as the number of comparisons involved are both linear, that is order of n. Then coming to the last, that is quicksort, with last element taken as the pivot. Now there are different strategies in quicksort. We can use the first element or the last element as the pivot, or we can go for the median as the pivot. In case the input is already sorted, then the first element and the last element taken as the pivot will give the worst performance. They will give order of n squared comparisons, whereas if we had gone for median or something else, then we would have reached the best case or the average case complexity or the number of comparisons in quicksort equal to order of n log n. But because we are taking the last element as the pivot, then it will give n square only for the sorted array. So again, this one gives order of n square comparisons. So which of the following is giving the least number of comparisons? That is the insertion sort algorithm. Its complexity as well as the number of comparisons required is linear, order of n, and it will involve 0 swaps for the already sorted input. So for this, the third one, that is insertion sort, will be true. This is a programming question. We have been given a C program, and for that we need to determine what will be the resulting scenario as it is given in the options. Let us check if this program compiles correctly and what is the result that it can give. So as it can be seen, there are 3 variables declared: I, j, and count. Count and I are both initialized to 0, while the third variable j, it is being used in this for loop. So in this loop, j runs from -3 to 3 and it's incremented by 1 in every step. So this loop will execute for the values of j equal to -3, -2, -1, 0, 1, 2 and 3. So this for loop will be executing for 7 times. And then inside that loop, what happens? We encounter this if condition. Now in this if condition, there are these two conditions. Let's call C1 and C2. There is an AND operator between them. So now when we check for two conditions, if C1 and C2, then because of the short circuiting property, what happens is if C1 is false, then we will not check for C2, we'll directly return false. But if C1 is true, then only we will check for C2, and then depending upon the result of C2, we will return either true or false. So that same thing applies over here. First we check for the condition C1, that is j greater than or equal to 0. Now this first condition C1, it fails for these three values. So in these three we check only for C1 and that fails, so we do not check for C2. So these three iterations of the for loop are simply wasted. Then while j becomes 0 and this onwards, the value of j will satisfy being greater than or equal to 0, which means C1 will be satisfied for these four values of j. Then only we will go and check for C2. And what is that? I plus plus. So for these four values of j, we will be checking for the condition C2. So let us check what happens for j equal to 0. Now as we can see, I also was 0 initially. So while j is 0 and I is also 0, we are at this point and we are checking C1, done. Coming to C2, if I plus plus. So if we have any condition like if I plus plus, then it checks for the value of I first and then increments it, because it is a post increment operation. So for if I plus plus, the initial value of I, that is 0, that will be considered in this iteration. So here we get I equal to 0 and then it is incremented to 1. So this if condition fails, which means for this particular iteration, condition C2 fails. So we will again not enter to this statement that is given after if. We will simply go to the next iteration of the for loop. And now I has become 1. So when we come to this j equal to 1 in the next iteration of the for loop, then C1 is definitely satisfied. Coming to C2, if I plus plus, here the value of I that will be considered will be 1. So now C2 is also satisfied, and for the next time I will be incremented to 2. So now because both the conditions have satisfied, we will execute this particular statement, that is count equal to count plus j. Count is initially 0. Now we are incrementing it by j. And what was j in this iteration? It was 1. So count becomes 1. Then we go to the next iteration. Here j is 2, I is 2. So both the conditions C1 and C2 are satisfied. If I plus plus, here the value of I is 2. So if 2, that is definitely true, because every boolean value other than 0 is assumed to be true. So if 2 means if I plus plus and if I is 2, then C2 will also be satisfied. And I will be incremented to 3 for the next iteration. So here both C1 and C2 satisfied. Again the statement will be executed, count equal to count plus j. So in this iteration j was 2, so that 2 will be added to count and it will become 3. So now coming to the last iteration, here j is 3, I is 3. Again both conditions are satisfied. The statement will be executed. J value is added to count, which means 1 plus 2 plus 3. Count becomes 6 now. And I is incremented to 4 for the next iteration. But then j becomes 4 and we will break out of the loop because it was only up to j less than or equal to 3. So now we come out of this for loop and then finally execute this particular line. This line will always be executed irrespective of the values of I and j. So what does it do? It adds the value of I to the count. What is I currently? It is 4. And what is the current value of count? It is 6. So to that 6 we add 4, and that gives us the final result as 10, and that will be printed. So what actually this code did, it added the value of j 3 times to count. What were those values? 1, 2 and 3. These 3 values of j were added to count, and then finally value of I was added to the count, which was 4 by that time. So 1, 2, 3 and 4 making up 10. This 10 was added to the count, and that is printed, which means the output printed by this code will be 10. So this program compiled successfully, and the output return will be 10 when it executes. So the correct option will be B to go with. This is a DBMS question based on relational databases. We have a relation R having attributes A and B in a relational database with 1200 tuples. The attribute A takes integer values ranging between 6 and 20. Similarly, the attribute B takes integer values in the range 1 to 20. We have to assume that the attributes A and B are independently distributed, which means they are independent of each other. There won't be implications like A implies B or something like that. So we can consider them to be independent events and accordingly evaluate them. So the estimated number of tuples in the output of this expression would be, is what to be determined. Now what is the saying? A greater than 10 or B equal to 18. So we can actually convert this question into a probability question, in which we can first evaluate the probability of this events taking place, and then find out from that what will be the total number of tuples from these 1200. We will only get a subset of tuples from these 1200, and that would be given by the probability of this event. So let us have event A denoting that value of A is greater than 10, and the event small b denoting that B takes the value 18. So what we have to evaluate is the probability of events A or B, which means A union B. So for this we can start with finding out their individual probabilities. P of A would be, A will take values greater than 10. From 6 to 20, it needs to take the values from 11 to 20. That will be the feasible solution. So it can take from 11 to 20, means 10 values out of all these. These are 15 values. So probability is 10 by 15, 2 by 3. Similarly, P of B can be calculated as, B will take only one value, that is 18. So only one possible solution out of these 20. So its probability is 1 by 20. Now we can go on to evaluate A intersection B. Means A is greater than 10 and B equal to 18. Both are taking place simultaneously. But since these events are independent, this probability will simply be the product of the two. So we get this as 2 by 3 times of 1 by 20. That gives us 1 by 30. Now what we can do is, we have the individual probabilities of A and B and of their intersection. So using these three, we can evaluate this one. It will be probability of A plus probability of B minus probability of A intersection B. So this is what its value will be. So we evaluate this thing. We can take their LCM as 60, 320 and 30. LCM is 60. That will give 2 times of 30 plus 1 times of 3 minus 1 times of 2. And we can evaluate this. It gives us 41 by 60. So this is the probability that this event takes place. A is greater than 10 or B equal to 18. So it means that out of 60 cases, out of 60 tuples, we'll be taking 41. But how many tuples do we have? 1200 tuples. So the estimated number of tuples that we will be having in the output will be this probability of events multiplied with the total number of tuples that we have. or simply put, it will be 41 by 60 times of 1200. This is the subset of tuples we'll be having as the answer. Calculating it, this is 20, so 41 into 20 gives us 820. So this is our answer. Out of 1200 tuples, we'll be having 820 those tuples in which this condition will be satisfied. So the estimated number of tuples in the output we will be having is 820. That is our answer. This is a TOC question. We have been given two languages, L1 and L2, where L1 is regular and L2 is context free. Now from the given options, the four languages are given to us, and from them we need to determine which of them is not context free. So let us check the options one by one. First one is saying L1 intersection L2. Now we know that L1 is regular and every regular language is also context free. So this is basically the intersection of two context free languages, which will also be context free because the CFLs are closed under intersection property. Now the next one is performing the concatenation operation between the two. Again, L1 can be considered to be context free, L2 is also context free. So their concatenation operation is given to us, and that will also be context free because it is closed under that as well. Then the third one is saying the difference between the two, L1 minus L2. So we can actually convert this L1 minus L2 into something like L1 intersection L2 complement, because from L1 we have to eliminate L2, and what this is doing, it is taking intersection of L1 with what is not there in L2, which means L2 complement. So both are equivalent. So if we convert the given expression into this form, then what is it doing? This L1 can be considered to be a CFL. This L2 is a CFL, but its complement, it may or may not be CFL, because CFL languages are not closed under complementation. If we consider L2 to be a CSL, context sensitive language, then its complement would also be CSL. But then we cannot guarantee if the intersection of a CFL with a CSL will be context free or not. Hence, this option can be said that it is not necessarily context free. It may or may not be. In the general sense, it will not be holding true. And then the last one is union operation of the two. CFLs are also closed under union. So again, this language will result into a CFL itself. So the only option is C, L1 minus L2, which we got to be not necessarily context free. So that will be our answer. This is a computer networks question based upon Hamming code. We have been given a 12-bit Hamming code word that consists of 8 data bits and 4 check bits. The sequence is given over here as it was there in the original question, but as you can see, if you count these bits, then it results into a 13-bit code word, just because there was a printing mistake in the question paper that this D4 is printed twice over here. So this was a printing mistake. We'll be ignoring that, and then this becomes a 12-bit code word that will be considered for calculation. So now the corresponding data bits and the check bits have been given to us in these tables, and we need to determine what would the values of these unknown bits X and Y. X corresponds to data bit D5 and Y corresponds to the check bit C8. So how we'll be proceeding with this? First, we need to note down that which check bit takes care of which position. And how do we do that? We make this particular table in which we have the entries for C1 to C8 from right to left, and we note down all the positions that are there 0 till 12, and then for whichever positions a particular check bit is set, for that positions it will be taking care of. What will it basically do? It will ensure that there is an even parity in those positions. So as we can see, C1 takes the value 1 at odd numbers, which means 1, 3, 5, 7, 9 and 11. So these positions in the code word will be handled by the check bit C1. It will ensure that there is an even parity in these positions. Similarly, we see that C2 is 1 at these positions, C4 at all 4, 5, 6, 7, 12 positions, and C8 at these remaining positions. So every position is handled by at least one check bit. Some can be handled by multiple check bits. As you can see, there is a 7 in all C1, C4 as well as C2. Similarly, 11 is there in C1, C2 as well as C8. So every position is handled by at least one check bit, and that is how we can detect errors in our message. So now how we'll be proceeding is, we have been given this particular sequence over here, and its corresponding bits can be found out from this table. So what we'll do is, we will create this particular representation in which we have first the given sequence, and in the next line in the green we have their corresponding bits. For data bits we will use this first table, and for check bits we'll be using this second table. So we write down their corresponding bits and we number them from right to left from 1 to 12. And now what we'll be doing is, we have to find out the values of x and y. Where is our x? Over here. It is at the position 9. So we will see that which check bit takes care of the 9th position. So as we can see over here, 9 is present only in C1 and C8. Similarly for y, it is at the position 8. Now this 8 is present only in C8 and in none other. So we are sure that if we ensure even parity because of the check bits C1 and C8, then we will be able to identify the values of x and y both. So let's do that. According to C1, the bits under consideration, the positions it checks are all the odd positions, 1, 3, 5, 7 and 11. So we will note down the bits on these positions. At position 1 we have the bit 0, then at 3 we have the bit 1, at 5 we have 0, at 7 we have 0, at 9 there is x, and at 11 there is a 1. So for these we will be doing the modulo 2 addition, which means it will be, the result would be made modulo by 2. So here as we can see, the result we are getting is x plus 2, and when we do the modulo 2 addition, this will simply convert to x. So now, because this position has to satisfy even parity because of this C1, what we'll say that the result should always be 0, then only even parity will be satisfied. And the result we are getting is x, which means the value of x itself has to be 0. Then only C1 bit will be able to ensure even parity in this position. So now we have got the value of x, and in the same way we'll be dealing with y as well. So for y, which means the position 8, it was present in only C8. So now we'll be doing the same thing for C8. Which are the positions that it is taking care of? From 8 onwards till 12, which means all of these in the box. So for these bits we'll be doing the modulo 2 addition, that is 1 plus 1 plus 0 plus x plus y. And what do we get? X plus y plus 2. On doing modulo 2 it will become simply x plus y, but we found out the value of x to be 0, so this converts simply to y. And again we have to ensure even parity because of C8 over here. The result we are getting is y. So for this to satisfy the even parity, again y has to be 0. So going with this method, we get both x and y to have the value as 0. Then only the thing will be satisfied. So what is the option that we are getting? The first one, option A, that x is 0 and y is also 0. That will be the answer. This is a digital logic question based upon counters. We are having a 3-bit counter that is designed explicitly using T flip-flops as it is shown over here. There are 3 T flip-flops connected to each other, TP, TQ and TR, forming a counter. So for this one, we have to assume that the initial state given by PQR is 000. All the inputs are 0 at the start. So what will be the next 3 states of this counter? That has to be determined. So how do we proceed for this? We'll be starting with determining the truth table of T flip-flop, and that we already know that if the value is 0, then the next state is given the same as the previous state, which means the latch state. While if it is 1, then we toggle. In this case, the next state Qn plus 1 will be the inverse of or the complement of Qn, given as Qn bar. So that is the truth table of the T flip-flop, and using that now we will be filling up this table, the initial state, which is already given to us in terms of PQR as 000. So from this we will be determining the current state and the next state. How do we get the current state? By looking at this diagram, as we can see this TP. Where does it get its value from? We will trace back this line and we can see that TP is taking its value from R, which means TP equal to R. Similarly, we can see that TQ, we trace this input. TQ is given as P complement. Similarly for TR, the value it is taking is this one, that is Q complement. So now using these, we will be filling the current states. So TP is R. So we simply copy this value of R from here, which is 0. For TQ, we need to take the P complement. P is 0, so P complement will be 1. And what about TR? TR is Q complement. So Q is 0, its complement will be 1. So 011 is the current state that we have got. And now based upon this, what will be the next states that we have to determine? So if TP is 0 and the input is also 0, then we'll be staying in the latch mode. Hence the value of TPN, which means the next state, will also be 0. Similarly, coming to Q, TQ is 1 and Q input is 0. So again, that is a latch mode. So TQN will be same as TQ, which is 1. And now coming to TRN, that is the next state for R. Again, we can see the input R is 0, so that will also be a latch mode. So the same input of TR will be copied over there. So the current state was 011 and the next state we got is also 011. So initially we were at this. The next state we got from 000 is 011. So now that becomes 011 comes here. Using that, now we'll be determining what is the current state and the next state. So let's apply the same thing. As we say, TP is R. Here R is 1, so TP will become 1. TQ will be P complement. P is 0, so its complement will be 1. And for TR, which is Q complement, Q is 1, so complement is 0. So we've got the current state. Now using this, we have to determine the next state. So coming to TP next, the input is 0, so that will be a latch mode. Hence, TP itself will be TP next, which is 1. Now coming to TQ next state, Q is 1, so this will be a toggle mode. In this case, TQN will be complement of TQ because of the toggle. So here TQ is 1, so TQN will be complement of it, which is 0. Similarly, coming to R, R is 1, so that will also be a toggle mode. TR is 0, so TR next will be 1. So the next state that we got from this is 101. From TPN, TQN and TRN, we got that as first it was 011, then it was 101. So we have got 2 states after 000. One more has to be determined because we wanted next 3 states. So moving on to the last one. Currently we have got 101 that comes over here. So now we determine the current state. TP is R, so it becomes 1. TQ is P complement, so 0. And TR is Q complement, that is 1. Now for the next state, P is 1, so toggle mode. TP is 1, so TP next becomes 0. Now Q is 0, so latch mode. TQ is 0, so TQN will also be 0. Now R is 1, so that is again toggle mode. TR is 1, so TR next will be 0. So the next state we got is again 000. So what are the three states that we got after 000? The first one was 011, this one. After that we got 101, and after that we came back to 000. Now will this be counted or not? Definitely it will be counted, because they asked us the next three states after 000. Now if we are coming back to 000, then it is also allowed. We'll simply be reporting the next three states as 011, 101 and 000. So as it is given in the option 4th, the last one, 011, 101. No, this one is not correct. We'll be going with the option first, 011, 101 and 000. So option 1 is the correct answer. Algorithms question. We have been given this P, which is an array containing n integers. Let us say this is our array P. It is having n integers. They can be anything. And let T be the lowest upper bound on the number of comparisons of the array elements that are required to find minimum and maximum values in an arbitrary array of an element. So by this arbitrary array, they mean the same array, that is P. So this is our array P. Nothing is given, so we'll assume it to be unsorted. And in this array, we need to find out the minimum and maximum elements using the least number of comparisons, and that number of comparison is denoted by T. So we want to minimize the value of T for this. So in this array element, because it is unsorted, if it were sorted, then we would say this is the first element, P of 0 is the minimum and P of n minus 1 is the maximum. That would take 0 comparisons to be precise. So we'll assume it to be unsorted and then find out the best algorithm which will give us the min and max elements from this array using minimum number of comparisons, and that number is given as T. So what are the different approaches we can go? The first one, the basic approach, if we go for linear search, that is, we will initialize the current max as, let's say, something as int min, and we'll initialize the current min as int max, and then we will traverse that entire array, and at any point, if that array element is found to be greater than current max, we'll update it. If it is found to be lesser than the current min, we will update that, and by the end we will have the current max and current min storing the actual maximum and minimal values in this array. But this approach performs a linear search, which means every array element is compared, so it takes linear number of comparisons, and that is what we need to minimize. So is there a better approach that will reduce the number of comparison? We need not check for every array element. Here we are comparing every element with both current max as well as current min. So that is what we need to minimize. So there is a better approach called as tournament method. It is an algorithm that divides the problem into two subproblems of equal size, and it says that, let us, this is our array P, then we'll divide it into two halves. Let us say this is the first half of the array P, and this is the second half, and it will continue till the end until we have the single elements or pair of elements left. Then from that pair we will find out the current max and current min. The smaller of them will be min and the greater of them will be max, and then we will keep on returning those values. So by the end, let us say at this particular level 1, we are having two equal parts of this array. In this we will have min and max. Similarly here we'll have min and max, and then both of them will be combined together to give us the min and max of the entire array. This will reduce the number of comparisons that we need. So this is a divide and conquer approach with which we can use the recurrence relation in order to find out the number of comparisons, and let us see how that can be done. The problem is being divided into two parts at a time. So let us say, in order to find out the maximum element, the number of comparisons that are required will be given as n by 2, n by 4, n by 8, and so on, because that is how subproblems are being divided. So this becomes an infinite geometric progression, and when we take its summation, we will take n by 2 as common, and then 1 plus half plus 1 by 4, so on. So this becomes infinite geometric progression with the value of r equal to half. So summation will be given as 1 by 1 minus half. That is becoming n by 2 times 1 by half means 2. So both of them get cancelled and we are getting n. So in order to find out the maximum element, we got n. And in the same way, if we were to find the minimum element, then what we'll do, we'll perform the same algorithm, but on the other half of the array. The size of the problem will be divided by half. So this thing will actually remain the same, but the input size has reduced to half. So that half will be carried out till the end, and hence for minimum, even the number of comparisons will be getting as n by 2, that is the half of the previous one. So what's the total number of comparisons that we needed? It is n plus n by 2, which means 3n by 2. So the value of t will be less than or equal to 3n by 2, but it will always be greater than n. So we can go for the third option, that is t is less than or equal to 3 times n by 2. This is the ceiling that they have used, 3 times n by 2. This is actually 3 times n by 2. So t is less than this, that's the maximum value, and the lower bound will be this n, because this is the number of comparisons that will be required in every case. So the correct option will be going with this, the third one. This is a DSA question based upon trees. We have been given a BST called T that contains n distinct elements, and from this tree we have to determine the complexity of picking up an element that is smaller than the maximum element. So we don't need to return the smallest element, we just want any element that is smaller than the maximum element of that tree. Now what is the BST? So let us consider different cases that can be possible. Let us say case 1, when there is just root, it has no children. Then coming to case 2, in this case 1, the root itself is the maximum element, right? And then coming to case 2, here we will have root and left subtree, something like this. So here again we can see the root itself is the maximum element. And now coming to case 3, when the root has both left subtree as well as the right subtree. Now in this case, root is not the maximum element, instead the last node in this right subtree will be the maximal element. So in all the 3 cases, let us determine what will be the result. So we need to find out an element that is smaller than the maximum. In case 1, we see that there is just the root that is maximal element itself, and there is no node that is smaller than that. So in this case, we will have to return null. But how will we check out that? We'll simply use the condition that if there is root left, if root is having the left subtree, if root left is also null, you can use this condition, root left is null, and similarly you will also check for root right is also null. If that is true, then you will return null. So there is no traversal involved in this code, it will simply take a constant time. So for case 1, we got a constant time. So now if this condition is not true, if both its left and right subtrees are not null, means they are existing, then you will check for the case 2, that if it is having left subtree but not the right subtree. So here again you can use the condition if root left is not null and root right is null. then that belongs to case 2. And again, this if condition will take a constant time. So once you are confirmed that it is case 2, then here what you will do, here you cannot return root because that is the maximal element. So in this case, you will return root left, which means this node 5 can be returned, and any below node can also be returned, but 5 is the first one that we encountered, which is smaller than the maximal, and returning 5 will only take a constant time. If you go on till the last node of this left subtree and then return that, then that will involve the entire traversal and it will take a linear time. But we just want an element that is smaller, so we'll go for the best case, that is return 5 itself, and that can be done in constant time. So for case 2 also we got a constant time. And then if this condition is also not satisfied, then you will check for this case 3, that both root left as well as root right are present. If that is the case, then you will understand that here root can definitely not be the maximum element because it is having a right subtree, and because this is a BST, then the right subtree of the root will have nodes having greater value than the root. So this root is definitely not the maximum element. So this root itself can be returned because this 10 or this root, this is the smaller element than maximum, that is 25. So here 10 can be written. There are other candidates as well that can be written, but going with the best one, the one which we encountered first, that is also allowed. So here we will simply return the root, and that can be done in constant time as well. So in all the three conditions, all the three cases, we got a constant time. How? We just need to execute one if condition, checking that if it is having left subtree or right subtree or none, that will definitely take a constant time. And then depending upon what has been returned by that if condition, we will be able to identify if it is case 1, 2 or 3. If it is 1, then you will have to return null because here there is no node that is having the value less than the maximum because this root itself is maximum. You can also add a case 0 there, that there is no root at all, but they have already given that T has n distinct elements, so there is no need of this. So then depending upon the result, we will be able to determine if it is case 1, 2 or 3 and then return the value accordingly. For case 1, return null. For case 2, return root left, that is the root of the left subtree, and for case 3, return the root itself. So that is how this problem can be solved in just a constant time. So the answer for this will be theta of 1.